let's go to an example on the so-called hedgers. Let's assume you own Apple stock in your portfolio. Let's say in your 401k or in your portfolio you have a bunch of Apple stocks. How would you hedge your position? By hedging means, let's say you have the Apple which is at 190 and you want to protect yourself. What happens because it's sitting on your 401k or it's sitting somewhere that in 6 months you may need money and you want to cash out? And what happens in the case that the stock goes lower? Then maybe face value today, if you have 100 of this, it looks as if you have $19,000 in your portfolio, but if it goes to 140, for example, then from 19,000 you go down to 14,000. Then what you would do is you would buy a put option because you want to now protect your so-called downside risk. And I'm going to give you an example exactly how that works. One more time, again, I'm asking this question. What's the benefit of buying the put option? The hedger, she protects the value of her portfolio against big drops in the value of the stock. As I said, that simply means protecting your downside risk. It's very important. Remember, in the case of a speculator did not own the stock. He or she was just speculating. Here, the hedger owns the stock and wants to protect the downside risk. Let's go over the example. Now, the hedger example. Again, we go with two scenarios. In the top one, the hedger did not buy a put option. Her today's portfolio is $19,000. I said it earlier. Why? Because today's price is $190, and my assumption is she owns 100 Apple stocks in her portfolio. Now, let's again go through the same scenarios. I mean, the scenarios here, I'm exaggerating actually even a bit more. Let's say future price, that means 3 months or 6 months from now, it could go down to 130, the worst case scenario, or go up to $250. Assuming that you don't have any protection, that means you're not hedging your position, what happens is future portfolio value, that means what happens 3 or 6 months from now, in this case would be $13,000 if it goes down to 130, $16,000, or the base case scenario would be $25,000. Remember, 13,000 with respect to 19,000, you're down $6,000 already. Now let's look at the case that the speculator bought a 6 months maturity put as a strike 180 and you paid $8 for that. Now one more time, you say why I'm paying $8? That's exactly what this options pricing module is trying to do, trying to help you to value the option. Why 8, why not 9, why not 7? We'll discuss this later. Let's assume that you bought a 6 months maturity, something that 6 months from now would expire, a put option with a strike 180, and you paid today $8 for it. That means today your immediate loss is minus $800. Immediate loss because you already paid that. That's out of your pocket. But let's look at the scenarios. Now, this is again today's price, 5 different scenarios. The worst case scenario going down to $130, the best case scenario going up to $250. But I'm going to go through each, and then what I want you to see is exactly how the hedging your position with a put option would help you with your downside risk. Let's go through it. The payoff. I'm saying the payoff here is $5,000 if it goes down to 130. Why? Because that would be different between 130, please do not say 190 because the strike is 180. That means what you would gain is 180 minus 130, which is 50 multiplied by 100 becomes $5,000. Remember, this is a put. That means when it goes below the strike, you make money. It's a put versus the call, which in the next slide, I'm actually going through a pictorial to explain to you how that works. Now, for this case, when it goes to 160, would be the difference between 160 and 180, which is your strike. You make $20 multiplied by 100 because it's on 100 stocks is $2,000. Now for the case of 190, because 190 is now above 180, the payoff is zero because you have the right. You're not going to exercise. You, in a way, it wouldn't make sense to exercise because it's a put option, and you never exercise anything which is below the strike price, which is 180. 0 and 0 for all of this. Now let's look at the future portfolio value. This is very important. Here is today's portfolio exactly as above. That's as far as this is your payoff, which you got it from here. This is the $800 that you paid that I say over here. Then if you sum all of this up, that would become $17,200, much better than this $13,000. The next case, again, the value of the portfolio was $16,000, exactly like here. $2,000 the payoff from here, and $800 that you paid day one. If you do that again, $17,200. Do not assume that's by accident it's $17,200. That's your cap on your downside risk. That means the value of the portfolio, no matter what, never goes below $17,200, which is not far from this, the worst case scenario below $19,000. By paying $800 today, you're protecting your downside risk. Let's look at the upside. On the upside here, no payoff from $19,000, which is the value of the portfolio, minus 800 is 18,200, 21 and 24. You may say, as you see, this is lower than this by 800. That's the premium you paid, but at least you're protecting your downside risk. Let's just summarize the observations. What was the effect of buying the put option for the hedger? By buying the put option, she hedged her position as the portfolio value would never go below a certain level. For us, that certain level was $17,200. No matter what, no matter how low the Apple stock goes. That's actually how people, and you could imagine a portfolio manager, when it comes to her portfolio, she actively hedging all the positions she's having on behalf of her clients. She has tons of Apples, Microsoft, Facebook, other stocks, and actually what she would do is she would go out there and actually would hedge the positions by buying various different put options on those stocks that she has in her portfolio. Of course, if you have just 100 of them, you buy one option, or depends, maybe a fractional, we'll discuss this later, but if you have thousands of them, then definitely you would go to buying 10 call options. Thank you. Welcome to lecture 3 on options pricing via transform techniques. I'm borrowing the last slide of the previous lecture, which was how to price a call option, and simply that was a formula that we had the discounted value of this integral, which this integral is simply the payoff of the call option multiplied by its conditional probability distribution over all possible values for S, which would be from 0 to infinity. And of course, to get rid of this positive part, we just need to go from k to infinity, which makes this one now non-negative. That means we can simply drop that positive sign, which is the positive part. Now, what we are trying to do is now we're trying to evaluate this integral, and there might be a case that we can do it actually analytically, but for this case, considering that we might have various different f, and it's not as easy to do it analytically, the goal is to actually do the evaluation numerically. Now then in the next 5 slides, I will be just discussing the evaluation of the integral. Now the very first question would come in mind is how to do it. Then definitely in case of call options, we need to make it a definite integral because it goes from k to infinity for the case of a call. For the put, it would be actually 0 to k, that we are okay because it's already a definite integral. Now, then the first thing is, as I said, we have to make it to a definite integral, and that simply means as opposed to going to infinity, we will go to some large number like b to be determined. Now then after that, when we have say k to b, what we are doing is we're dividing it into n equal sub-intervals, and then over each of those sub-intervals we have a sub-integral, and we evaluate each sub-integral, again by evaluation means numerical evaluation, and we add them up. That's what I'm trying to explain to you, how to do it numerically. And then going from k to infinity, we going from k to b large enough, and as you see, equality becomes an approximation. Then definitely as b approaches infinity, this would approach the true value, but if b is large enough, what we are missing is very insignificant. That means we can easily neglect it. Now, the evaluation of the integral, I'm distinguishing between the call options versus the put options. Now, what I would do is, this is the way I would do it. That's not the only way to do it. The way I would do it is I would choose eta, which is the length of each sub-intervals, and n independently. That means what happens is I'm not picking b, I'm picking eta and n, and then I would know what b would be, which the way I would set it up is I would set grid points starting definitely from k going to b, which the way I'm looking at the b is I'm setting up the grid as k plus j minus 1 eta, and j goes from 1. In case of a 1, of course, the first starting would be k to n plus 1, which would substitute here would be k plus n eta, which this k plus n eta is what I will be calling b, exactly as I'm explaining it here, and that becomes our upper bound. As I said, eta and n are chosen independently. Now, in the case of put options, actually, that's not the case because we already know the upper bound, k. Then what we would doing is we just choose n, and eta would become nothing but k minus 0 divided by n, and that becomes your eta. And then the way you would set up the grid points simply would be going from 0, as I'm saying, maybe you should have written this one that way, 0 plus j minus 1 eta, exactly like this, except here it was going from k to b. Here is already known that the minute that you go to n eta, that n eta becomes the k that we have. I just want to make sure that you distinguish between these two, and you will see it in the Python code. Actually, I'm actually respecting that as well. Now, setting that one up, then what we are having is we have the sub-intervals, say one of them would be sj to sj plus 1, and we have n of these. That's why I'm writing that approximation that we had. This, I'm rewriting this as that one now, which you're saying would be n of these sub-integrals. That's exactly what we mean, over each of these sub-intervals. Now I'm taking one of those out, and I'm trying to evaluate it. And what I would do for evaluation is I'm using actually trapezoidal rule. Simply means going back again to this, I'm assuming this is sj, this is sj plus 1. I'm going to exaggerate a bit. Let's assume this is what you're trying to find, the area underneath. That's what integral means. But as opposed to finding it analytically, I'm assuming I'm finding the area underneath, but using trapezoidal rule. Exactly like that. That means I'm adding this to that, multiplying it by this one, the length, which is eta divided by 2. That's exactly the eta divided by 2. This one is the length over here, which means simply be substituting Sj here. That's what I'm doing. And then the other one would be exact same thing evaluated at Sj plus 1. What I'm missing is this part. This is what we are missing in our approximation. And then remember, as eta gets smaller, definitely our approximation to become more accurate. And you're gonna see it because I have some numerical examples for you. Now we simply substitute this one back into the sum, which is I'm rewriting it here. That means for this one, I'm substituting this approximation for it via trapezoidal rule. And what you can do is, if you expand this, because now you're having inside sum, you have this plus that, but if you expand them and sum it up, you will actually get just this expression for Wj being eta over 2 in the case of J1, otherwise eta. That should be clear. The reason for it is because the neighboring trapezoid, if you look at it one more time, something like this. This one not in common, that one is not in common, but this would be in common. That is why when you're doing eta divided by 2 in trapezoid, this gets counted twice. That's why anywhere else you would get eta except for the very first one and the very, very last one. You may ask me what happened to the very, very last one. I'm not seeing it here. I actually dropped it. The reason I can drop it is because I'm saying that it's so small enough that I can neglect it. I'm going to leave this one as an exercise. What I would do is when I'm setting up the quiz problems, I actually want you to actually explore this, which you can do it easily in one line. Now let's make sure we understand the computational cost. By computational cost, I mean roughly if this operation, I call it as one operation, how many of those operations should I do? That would be n of them. That is why the operation cost is O n. It's very, very important for us because as you will see later on when we're trying to do say m other options, that means with this method, operations would become m multiplied by n. That's very important to know because for each option, if it's O(n), for m options, that would O(m)(n). It's always important to keep track of computational costs. Now, I would do exact same thing now for put without going through the entire derivation. Simply would be exactly the same of a call except for k minus sj. And of course, you already know how we set up the sj for the put if you go back to the previous slides, which also in the Python code, you will see exactly the way I have done it. Exact same computational cost too, exact same one. Now, let's go through the example. First, I'm going through the example, then I'm going to go through the Python code. For the example, I'm looking at the simplest possible case, which is a case of a log normal distribution. Log normal distribution is a distribution for geometric Brownian motion. If you assume your process is geometric Brownian motion, if you don't know it, that's fine. What I'm saying is this is one of the simplest processes that we assume for evolution of a stock price process. Another name people use for it is actually Black-Merton shoals. Now, for the log normal distribution, which again conditional probability density function given a spot today, distribution of a spot in future. Of course, future depends on time t, which it will show, it was showing up here and there. And then I'm assuming for the stock, there is a interest rate and dividend rate, which I'm having it here. Volatility, which was showing up 3 different places here and there. Now, the final, the starting point, the final point, which will show up 2 places, and the rest is just a matter of exact definition of log normal distribution. The interest is actually exploring that, what that one is. I'm assuming this is given to you. What you're asked is price the option for it, call and the put. Now, before we move to the next step and showing you the results, it's very important to recognize, depending on what today's spot is, you may see a different shape. For example, I'm having 4 different shapes here for you. Now, this one, the blue one, is the case that the spot today is 50, as you see, is jammed around the 50, or at least you will see a big pick. It gets flattened out as the spot started moving to the right. For example, for the case, this is the flattest one, this red one you see is for the case that the spot today is 200, as you see, is much flatter than the one that is 50. It's very, very important, because if you're starting at 50, for you to get to 100, probability is much, much lower than you start from 200 and you want to get to, say, 220 or 230. That's why it's much flatter. Good. Now, for this case, for the problem I'm going to have in mind, I'm assuming today's spot is 100, risk-free rate is 5%. I'm assuming dividend rate is 1%. And of course, you can play with it yourself in this environment. Today, people assume typically interest rate of being about 2.5% or something like that. I just assume being 5%. Maturity of 1 year, assuming T is 1. Again, you can change it to anything you like. Volatility 30% or 0.03. And the strike of 140. Again, you can change it to whatever number you like. This is just for the example I'm having. Now for the call, as I said, for the call, I'm picking N and eta independently. Then what I'm doing here is I'm having various different values of N, and I'm showing all as 2 to the power. I don't have to do it this way. The reason is because that's my habit, specifically when we go into other methods you will see. And eta, I'm assuming from just 0.25, which is 25 cents, going to $1. That means when it comes to breaking it down into sub-intervals, that would be your step size. And then definitely you can build your KB, which would be K plus N eta. I don't have to emphasize on this one in the case of a call. You remember we mentioned this earlier. Now, for this one, I'm simply showing what you would get from that numerical integration, or the so-called approximation. And these are the values that I'm having actually. I'm going through all of it. The only thing is using some of them I'm putting in the yellow. That means that's the exact answer is actually, if I'm not mistaken, is this. How do I know it? Because for this case, we have the analytical one. As you see, for most cases, we've done extremely well, except we are off here and we are off here, which simply means you need to make sure that, because maybe here B wasn't big enough, large enough, because if you substitute them and maybe B wasn't large enough, but the rest of them you see is large enough and the step size is good enough that you get a very good, accurate approximation. Then, as I said, that was the call prices were struck of 140, which is out of the money call for various values of eta and N, and overall we've done a good job. Let's go to the case for the put. For the put, as I said, we are just picking or choosing N, and we would have implied eta, which was simply doing K divided by N. Do not forget, that's why when I'm having various different N, I simply getting eta, which would be the 140 divided, say, 2 to the power 8. If you do that, that's what you would get. And the rest as well. Now, the premium I'm getting, actually, these are the premium. And as you see, for all, actually, we're doing a very good job. They all, I'm putting in the yellow one. It's, they actually pretty tight for the in the money case, because when we have in the money, out of the money call for the same strike, the put become in the money. Now, before we end the lecture and we go through the Python code, let's do an assessment of this approach. The very first question is, how good is or how good was this approximation? For appropriate choices of N and eta, the approximation is pretty good. Actually, it was pretty tight. How feasible is this approach? That's the second question. The thing is this: if you have the conditional probability density function in closed form, you have it analytically, and it's not that expensive to calculate it, because there's some cases you might have it but it becomes expensive to calculate it, is absolutely feasible, is actually feasible. But in most cases it turns out that it might not be available in an integrated form or in closed form, then overall this approach is not feasible. I just wanted to say, if you have it, definitely you have a way to do it. If you do not have it, you should think about an alternative way. The next question immediately after that is there an alternative or a better approach? The answer is yes. That's exactly what I'm having in mind to go over for the next 4 lectures, which we'll be starting transform techniques. Then what I'm going to do is I'm going to go over the Python code, and what I did in those 2 tables, the population and all of it that I did, I'm going to actually go through the code and explain to you how to do it. Now I'm going over the Python code. I'm having one for just plotting the log normal for various spots. Is important if you want to just play with it. And the other one, I'm going to go actually through the options pricing by that numerical integration in case of having the conditional probability density function. Now, this one is just simply what I call plot log normal for various spot prices. This is simply just importing NumB, shift enter. Here are the fixed parameters, the interest rate of 5%, dividend of 1%. Somehow I have sigma of 50%, doesn't make a difference, and T of 1, that's fine. Model log normal, this is just, at this point, is not really doing anything. It's just model on the quantization. That's the implementation of log normal, which I have it as a helper. That's just exactly that. Now, plotting density for various snot. Then what I'm doing is I'm actually first making various different for final stock prices. I'm going to say from 0.025, which is 25 cents, to roughly would be what 350 something. And I first make that grid, and I'm passing that through that helper for various different spot prices. As you see, 50, 100, 150, and 200. There are better ways of doing it. This is just for illustrative purposes. Done. And what I'm doing is just simply plot it. And that's exactly what I had for you guys on the slides. As you see, the blue one is for the case of 50, orange one is to 100, green 150, and 200 for the red one. And let me see, that's it. That would be the code for, and then of course that one is just simply good. This is just, yes, that's the same thing. Fantastic. In the other code, what I would be doing is, as I said, I'm going to walk you through the options pricing by numerical integration in case that we have the conditional probability density function. Let me switch to that one now. Again, that part is the same, no change, except I'm just measuring also time. I just want to see how fast I can evaluate that integral. Fixed parameters. Now, anyway, let me change this to 140. My apologies, that's 140. Good. Then the spot 100, 140 strike, and interest rate 5%, dividend rate 1%, sigma 30%, and maturity 1. This doesn't do anything, but still I'm just having it there, the same helper as before. Now evaluate integral. For that one, I'm getting the arguments, which are R, Q, S naught, K, sigma, T, N, and DS. DS is exactly the same as eta, just calling it ES. And discount factor, of course, once you have R and T, you would have the discount factor, fine. Now, in evaluation of the integral, if you remember, we used trapezoidal rule, fine. Calls and puts are different, as you remember. For a call option, we integrate from K to B. And the way I'm setting it up, I'm actually, once we have DS or the same as eta, maybe I should have changed it to eta, I'm setting up the grid which goes from K to b, which b in this case would become k plus n eta, as you remember. That's what I'm doing here. Let me give it a bit of a space for it not to get jammed up too much. Fine. Now, once I have this s, I can pass it in and get a vector for temp, which are all possible values for this f of s given s naught. That's fine as well. I'm setting up the wj. If you remember, for the first case, it was eta divided by 2 or ds divided by 2. In the last case, it was ds. That's fine as well. And then what I would doing is, I'm setting up a sum. I could have actually have this one over here. Should not, could be, oh, sorry. Let me put this one here just to make sure that it is sitting exactly before we start. Not that it makes any difference, but I want to be tighter. Good. Then what I'm doing is, I'm starting from 0 and I evaluate each of those sub-integrals and I'm adding it up. And if you remember, the way I put it was sj minus k multiplied by the f of s given s naught multiplied by wj, which is depending on you're at 0 or the one after that. When that's done, at the very, very end, you just discount it. That's exactly how I would evaluate the call. For the put, it is almost the same, except the way we're setting up the grid. One more time, if you remember, for eta, it is k divided by n. But knowing that we don't want to start from 0, I call it k minus, you know what, I actually don't even have to do this. That's fine. I can just simply make it like that. That's okay. But I would never want to start from 0, because then it would make it undefined. I start from something tiny when it comes to evaluation of the conditional density. You can actually try it yourself. I can set up as a quiz problem too. Then the grid would be from, say, almost 0, which is something tiny like 10 cents, and then going to n multiplied by eta. And don't forget, the reason we're having that one is because the upper bound is n eta, which becomes k. You remember that. Again, we send it through this density to get all conditional densities on each grid points, passing it through this loop. And again, I see, again, I should have put this one over here, which, as I said, no difference whatsoever, just makes it a bit cleaner. And this, I'm doing exact same things, summing up, evaluating each of those sub-integrals. I'm summing it up and discounting. That's very, very consistent to exactly what we discussed during the lecture. Very, very consistent. And you have the code. You can play with it yourself. That's also done. And now it's time for me to, let's say, for example, for N8 or 9, doesn't make a difference. I do just pricing, and that becomes my pricing. And you can go through the slides and see these are exactly the values that I populated in those slides for puts and calls. The first one is the put, the second one is the call. And look, the time it took us to evaluate it. The time is actually 8 thousandths of a second. It's actually pretty quick, pretty fast, sorry. One more time, the question should ask yourself, if we do have the conditional probability density function, if we do have it, if it's not that expensive to evaluate it, of course, this one wasn't expensive, as you see, it's pretty fast, then this method actually pretty feasible. But in general, that's not the case. And that's exactly what we will go over it in the next lecture. Thank you. Let's go through the setup. As usual, we assume S cap t is t time price. That means the price at time t, which is unknown, of course. Now, as before, we assume that we have the density of SC. Remember, you say, oh, but you said we don't have it. The assumption is we say that assume that we have it, and then you'll see that we actually wouldn't need to have it. Now, when we write the density of ST, but we typically work in the log space, then when it comes to the density of log of ST, which we call it at the smallest t, is what I call K, then Q, sorry. Then I go from F to Q. Now also I'm working in the log space for the strike as well. I call it a small k, which is a log of capital K. This one, as we said it earlier, is a characteristic function of the log of the stock price process. Fine. Now I'm kind of abusing the notation here. Previously, what we call a call, we write it like this, if you remember in the previous lectures. Now here, a bit for simplicity and also because we work in the log space, I'm writing it as CT small k. This is exactly the same thing, except I'm having this one over here. As opposed to capital K, I'm having the small k, which is a log of k, and I'm dropping that 0 is known, that is today's price. This is just a notation. I'm sorry that I'm abusing it, but this is what we typically intend to do. The CTK is the price of a T maturity call with this strike, capital K, which is e to the power small k. Now, what's the formulation? As before, you've seen this before. It is the discounted, you remember this expectation, which that expectation was exactly this. You remember when we dropped the positive part, it turned to this. That's exactly what I'm borrowing from the previous slides. Now I'm turning everything from capital S K to its so-called log space. Then instead of st, I'm writing it at e to power small st, k, I'm writing it into e to the power k. This one, as I said, would become q, and that one, of course, I'm changing. Remember, when you go from here to this, you do the change of a variable. That means you go from s to the log of s, which is s. And that is what I will be calling that one. This is just simply starting what we have, do the change of variable, do everything in the log space. Good. Now, just for you to see the relationship between f and q, you already seen this for the log normal distribution. You've seen that before in the previous lecture. In this lecture, when I'm going from f to q, it looks like this. You may say this is exactly the same because this is what is exactly that. This is exactly what is exactly this. The only difference is, as you see, there is no st in the denominator and a log in the denominator. The reason is because you do the change of a variable, that would be gone. I'm going to leave this one as an exercise for you, actually. When we set up the exercise or the quiz, I'm going to ask you to do this, which is a simple change of a variable, just in one liner, but it's a good exercise for you to do it. Now, as I said, the goal for us is to link the characteristic function to options pricing. Then the next few slides is just, I'm going to do step by step, just some derivation. And after it's all done, as you see at the end, I come up with a generic form of pricing, which would be a nice, simple, model-free setup. But I have to go through some derivation just to see how we're going to link it. A few things I'm going to do. The first thing is this. I already started from CTK, but I wouldn't work with CTK. I would work with the small CTK, which I call it the so-called modified call, which the modified call means the original call multiplied by this. You may see later where this is coming from. At this point, just take it for granted. This is just E alpha to K, which the K is the same K, and alpha is some positive number. Now, what I will do is I'm going to look at the Fourier transform of this modified call. Then the Fourier transform of modified call, which I'm going to call it psi sub t nu, and I'm using the definition. Then the definition of Fourier transform was simply this, multiply whatever you want to get. If you remember, for f of x, that was his Fourier transform. Then instead of f, I'm substituting this, nothing more. And then what I'm doing is, of course, it itself means that. I just did a simple substitution. Now, let's say you have this. Then what I said, if you have this, to recover, and my apologies, let's say you have this one is given to you. In order to recover CTK, we just do inverse Fourier transform. I'm just using the definition, and if you remember, it was 1 over 2 pi, whatever that one is, but considering this was coming out, that's exactly where this is coming, and remember, it becomes the reverse of it. Then it's 1 over 2 pi, and of course this one, assuming this is known, and that's exactly by definition. That's, if you go back to the slides that I had the definition of Fourier transform, inverse Fourier transform, that's exactly where it's coming from, assuming you have that. You may say a few things. First of all, I do not have this. That's correct, but you will see you're going to get it actually analytically, and that means you're going to get that one once you have that one. Good. Let's see, then what I would do is I'm trying to get this one analytically, which it was exactly that. I do simple substitution. The simple substitution is this, remember we had the E alpha K, and the rest of it comes from the definition of the call, which is exactly what we had in the previous 2 slides. Now, I want to evaluate this one. In order to evaluate it, you'll see actually we are at the dead end. We can't go any further than this. But what I'm trying to do is this. I see what I can take out. What I can take out is this. This one comes out. By taking out means no dependency on S or on K. Remember, this becomes a double integral after the substitution. Now, the other thing is I can make this 2 into that form. Nothing new here. But what I'm doing is the integral was going from minus infinity to infinity, from k to infinity, ds dk. What I'm trying to do is I'm trying to do the change of integral, which is called Fubini. Fubini would tell us how to do this. Then as opposed to going from minus infinity to plus infinity, k to infinity ds dk, this turns out to be minus infinity to infinity, minus infinity to s dk ds. I'm leaving this one as an exercise for you as well. Again, it's just a 2-liner. You're simply looking at the way you do integration, you're just turning it around, and then you will see you come to this term. That's exactly what I did. This coming from here to this, I'm using Fubini. Fubini theorem would help us to do the change of integration. Why this is important for us? Because the minute you do the change of integration, then you see this QS does not depend on k. When you do the integration first with respect to k, that means you can pull it out. That's exactly what I did here. And whatever I'm leaving over here are those that depends on k. The rest, I'm taking it out. And then you'll see I can take this integral analytically, which I'm showing it in the next slide. Then in the next slide, what I'm doing is I'm taking that integral out, I'm doing the integration, I do the substitution, and that's where I'm ending. Now, what you would notice is if you didn't have this alpha, that means if you go ahead and set alpha equal to 0, this 2 would have been undefined. Again, another exercise, I'm leaving it for you. That if you set alpha equal to 0, you do the substitution at minus infinity, it would be undefined. Having alpha greater than 0 there, for any alpha greater than 0, theoretically, you will see it would vanish, it would be 0. That's why it would be this evaluated at S, this evaluated at S, common denominator, I would get that one out. And as you're noticing, that inner integral now I've known analytically, I can substitute it back. By substituting back, that's what I would get after the substitution. And I can take the denominator out because it doesn't depend on S. That's the denominator is out. This one is already out. And then you'll see I end up with this integral. You may see, hold on, but I cannot do this and this one analytically. The answer to it is yes at this point, but you already know the characteristic function of log of the stock price. The characteristic function is this. That's the definition of characteristic function, which is this. You already have this. Once you have this, then you will notice that this is nothing but this characteristic function being evaluated at this point. And then as you will see, the Fourier transform by modified call can be known analytically as long as you have the characteristic function of the log of the stock price process. That's the beauty of this. Now you already got this one, and as I said earlier, in order to get the callback, it would become nothing but this e minus alpha k divided by 2 pi minus infinity to infinity of e minus I nu k multiplied by this, which I put it in a box because I know it analytically, and do not forget what that one is. This is this. I'm going to end up, I'm going to just let it be for this lecture. In the next lecture, what we're trying to do is, now we're trying to evaluate this one. But as you see, the call is linked to characteristic function through that one, which I'm going to substitute it in and explain to you how to do it. See you in the next lecture. Welcome to lecture 5 on option pricing via transform techniques. In the last lecture, we actually ended with, I'm borrowing, as usual, this is my habit, I'm borrowing the very last slide of the previous lecture. Where we ended up was call option via inverse Fourier transform. If you remember, I said once you have this, which was the Fourier transform of modified call, Fourier transform of modified call, we said we can evaluate the call option via this integration. And if you remember, as you remember, I would say, the Fourier transform modified call, which is this, we have it with respect to the characteristic function of the log of stock price process. That means once you have this, once you have it, the characteristic function of the log of the process, the stock price process, and we evaluate it at this point and multiply it by this quantity, what we would get is, we would get the Fourier transform of modified call. That means we have it in an integrated form. And to get the call, we simply do the evaluation of this integral. But how would you evaluate this integral? Then what I will do in the next 3 slides, we will discuss integral evaluation. Now, we have this now, knowing that this is known analytically. As we did it before in lecture 3, we do not like to deal with indefinite integral. We want to be definite. That means what we are saying is, as opposed to going to infinity, we will go to b. You might wonder what happened from minus infinity to infinity, which I have 1 over 2 pi. I move to 1 over pi, 0 to infinity. The reason for it is because we have an even function. The integrand was an even function. I wanted to leave this one as a short quiz problem. For the even functions, what we can do is, if we have it minus infinity to infinity, it would become, as you see, instead of 1 over 2 pi, it becomes 1 over pi, and instead of minus infinity to infinity, it becomes 0 to infinity. That's the first thing. Now, we want to make it a definite integral. We simply go to something large enough, hopefully b is large enough, such that by ignoring the rest of the integral, I'm not going to lose much. It's within some threshold. And then the b to be determined, actually, and is 0 to b, and the same integral, except is now definite. Now, what we are trying to do, we're trying to evaluate that integral. We've seen already integral evaluation. Then I'm using exact same method. Again, as we did it before, we are familiar with this. We set n equals subintervals of length eta. I'm trying to be consistent with what we had before. That makes it easier that way. And what we are doing is, we're saying eta is b divided by n, and that becomes your grids, the grid points, because now we are going from 0 to b. We set it to n equals subintervals, And what we're doing is, because this is over nu, the first one is nu 1. This comes to nu n plus 1. And these are your grid points. And do not forget this length is eta. Eta, and that's how I'm setting up the grid points. And this is just the way it is easier to write it the way I'm writing it. You could have said something like this is equal to j eta, and instead of 1 you could start from 0. These are different conventions, up to you, but these make it easier, as you will see later on, to write it the way I'm writing it. Now then what I'm doing is, it goes to n subintegrals, and each subintegral looks like this. This is very consistent to the way I did it for the case that we have the conditional probability density function. Now we go to each subintegral using trapezoidal rule exactly as before. Again, just to remind you one more time, the way it works is, if we have this as one of the sub interval, and let's assume we have something like this, I turn it into a trapezoid, and I do the area of this trapezoid. And what I would missing is, because this is not exactly the area underneath, this is how much I will be missing. But what I'm saying is, if eta is small enough, because this length is eta, this would be a very tight approximation. That's what we are doing here. One more time again, that would be simply this height plus this height multiplied by this length divided by 2. That's that part. And then of course this height means this integrand evaluated at nu j. This simply means is at this height, which means this integrand evaluated at this point and it. That's, as I said, very consistent to what we had before. Now I'm simply rewriting what I had for the subintegrals. Now I'm substituting for this what I'm getting up here, which would come down here. And as I said before, now we have a sum, but inside sum I have two quantities. I can turn it into one by just simply expanding it. And when I'm expanding it, I can write it as 1. The only difference is, because, one more time as I said it before, because when I'm writing the trapezoids, the very first one and the very last one wouldn't share this, but the one in between would share the height twice. That means the one in the beginning and at the end would have eta over 2, but the one in the middle would have just eta, because I'm utilizing them twice. You might say, I'm seeing the first one, what happens to the last one? I dropped it. That means this sum, as you see, does not go to n plus 1. I dropped the last one because I'm saying I can ignore it. And you'll see later on that would be very helpful for us to do. Now, as we did it before, we always look at computational costs. If we call each of these as one unit of computation, how many units would you use? You would use n of them. That means it would be order of O n, O capital N. Now, I want to do a comparison. Now, what I mean by comparison, in the case of having the characteristic function, this would be a function of characteristic function. You already seen this. And that would give you the option price. This is versus the case of you having this is, I'm borrowing from lecture 3. I'm having the conditional probability density function, versus this. These two, computational wise, looks like they both are ON. This is very explicit. Explicitly you see it, because that's simply the payoff. That's simply the conditional PDF. And actually these weights are exactly the same as before. The cost looks the same. But as you see, this is pretty actually implicit, because you don't see any payoff, you don't see any PDF, you don't see anything like that. But it turns out actually this becomes more generic than the other one. The reason is because for most processes, we do have characteristic function of the log stock price, as you will see in the next lecture, and it's easy to calculate. We have it in integrated form, but when it comes to the PDF, that's not the case. That is why we switched. And when you compare it, this is fully explicit. By explicit mean explicit, you can see the terms. This is pretty implicit. You can actually see that it's actually looks like a call price. Having said this, the derivation comes from it, and you've seen actually the derivation. Now, what I will be doing in the next lecture is that I'm now trying to explain to you that what's the benefit of utilizing this as opposed to the other one, aside from the fact that in many cases we may not have conditional PDF. There are other benefits to it as well. Until next lecture. Thank you. Welcome to Option Pricing via Transform Techniques, Lecture 6. In the previous lecture, we explained how to, first of all, we linked the option pricing to characteristic function via transform technique. We went through it, and if we are interested in just pricing an option, say at some maturity with just one strike, we are done. We don't need to go any further. We have a way of doing it. We did the comparison and all of it. And definitely what I will do is I already have a sample code, a Python sample code on implementation of what we discussed in lecture 5. But before I go through that, in lecture 6, what I want to actually go over is what happens if you are interested in finding options prices for at one maturity as a single maturity, but various different strikes. You might say what we would do is, as I mentioned, you just use exact same technique, say m times, which the computational cost, if you recall, would be O, big O, m multiplied by n, which n was the computational cost for one strike, and then if you want to get m strikes, would become OMN. But how about if I say that there is a way that we can actually make that cost much lower, much lower? Then this lecture is continuation of previous lecture, emphasizing how about calls or puts. Remember, when I'm saying calls, I mean puts as well, but I'm leaving puts up to you. What I'm saying is, for your quiz or for your exam, I'm going to explain to you by just one simple change, you can go from calls to puts using exact same technique that I'm describing here. Then how about calls with various strikes? Then one more time, let me just recap. If you are interested in just one specific strike, no extra step is needed. Then no extra step is needed. That simply means we could have stopped at lecture 5, we wouldn't need lecture 6 or lecture 7. But how about calculating option premium at that maturity, which is a fixed maturity, for various different strikes? Assuming, for example, m strikes, as I said, we repeat the procedure m times, and computational cost, as I said it earlier, would be OMN. However, there is a method that we can use that would reduce that cost tremendously. And what we are trying to do here is we are trying to use actually what is called FFT, fast Fourier transform, to get premium at n different strikes with the cost of ON log n as opposed to ON square. You may say, why not m, why n, which is the same n? Because that's the way FFT works, as you will see. When I'm saying FFT in all programming languages, we have actually FFT built in MATLAB, Python, C++, Java, all. We were looking at that as a black box, but I'm going to actually go through its description. I'm having a sample code for you, explaining how it works, but then we will take it for granted. We're just calling the FFT routine in Python to do the job. Now, call with various strikes. Let me go through the formulation we had end of lecture 5. And then what I'm doing is I'm just changing, as you're noticing, I'm just changing the K that we had to Km, knowing that now we have M different strikes. Then the formulation is exactly same except for the Km. That means if you go back to last slide of previous lecture, lecture 5, you're seeing this formula is exactly what we had there, except now instead of just a fixed K, I'm writing it as Km for M going from 1 to N, which I'm going to explain to you. I'm going to set this one up. Now, what I would do is this. When I'm having this one over here, what I can do is now I can actually write this Km as something like this: beta plus M minus 1 delta K. Then what I'm doing is I've instead of fixed K's, I'm running into an array of K, and that's the way I'm introducing them. You may say, why do I need beta? Beta would be the starting point for the very, very first strike. And that is why, and beta is up to you, you're gonna pick beta. And then what you're doing is M minus K, the delta K, which would be the step sizes for the stepping size for log space of those strikes. And then typically what we are doing is we're replacing this delta K, as you will see, with just lambda, for simplicity. Now, then if I go ahead and substitute this one over here, it will carry it into the next line. And do not forget this, for new J, I had J minus 1 eta. That's what I had for new J already. Now for Km, I'm having beta plus M minus 1 delta, which delta was, lambda. Lambda was delta K. I'm just substituting in, and this is what I would get, this term. This is, of course, been sitting already here. No change to these two, which is simply carrying from over here. And the substitution and taking the beta out, this is what I would get. But you're noticing something, and that is this quantity does not depend on M at all. That is why I put it in a box. And you see in the next slide, this is what I would call xj. Again, I'm doing all of this just for simplicity. Now, by substituting that one in, and then simply putting these two over in front, which, as I said, the delta K is lambda, then I would get minus I lambda eta J minus 1, M minus 1, multiplied by this quantity, which I would call it just xj. Let's go to the next slide. And that's exactly how this would look like. Now, as you will see, for M from 1 to N, see the call prices for Km for each of those would be simply what I'm having here. As you see in this case, it's still sitting here, but then I carry it through, and that disappears because now I'm just simply substitute this for it. That's exactly what I will be having. You may say, so what, you did all of this, where we heading with this? The way we are heading is this, that the definition of fast Fourier is this, the fast Fourier transform. FFT, fast Fourier transform, provides, as I said, these are already built into Python and most programming languages. FFT provides an efficient algorithm for calculating this sum. For this sum, you may assume that because I'm having n here, it would be On, then I'm having n here, it would be On square, because I'm doing n of those. But fast Fourier transform does this, as opposed to On square would do it as On log n, as I said that earlier. I'm not going to go through the proof. That's a known fact. There are papers written in it, but we don't have to bother with it. It's as if we have an engine. We know how the engine works. We just use the engine like a black box. Now you wonder, how do I go from what I had in the previous slide, which was this, to this one, and link him? The link is actually pretty easy. You will see I can link it simply by setting up lambda eta to be 2 pi over n. Let's go through. I'm asking two quick questions here. One is, what is its efficiency? Even though I said that earlier, I'm going to repeat myself. The computational cost becomes O n log n as opposed to O n squared. This is very important. I keep emphasizing this because what happens is, as you know, for n large, log n is pretty small. That means this becomes very efficient to work with. For n strikes, I would do it with just O n log n. By log, I mean actually natural log. Now, how can we use FFT? That simply means from the definition of FFT to what we had, how do we link him? The link is simply done by what you're seeing as lambda eta, by setting it to be 2 pi over n to make sure that we exactly get it to look like the FFT algorithm. Good. Now, let me just put everything together when it comes to implementation, start from scratch. Now, what we said is this. We said having characteristic function of log of the start price process. One more time, this characteristic function is given to you, is provided. And what we are building here is actually model-free setup. That means once you have that characteristic function, you don't have to do anything. You just pass it through and everything would work, exactly like a black box. We choose eta. That was clear. The eta was the shipping size that we did. We come up with n, which is typically we write it as 2 to the power small n. We also choose beta. As I said, beta has to do with you. It's your choice, which I'm going to go over that. We calculate lambda because once you set up eta and n, we have this constraint. This constraint was needed to link our calculation to FFT algorithm. Once you set this one up and that one up, then you get the implied lambda, which simply by solving it for lambda, which is 2 pi over n eta. That's exactly what I'm having here. We're setting the step sizes over space of nu, which if you remember was nu j, was j minus 1 eta. We set also alpha. You remember we have that damping factor, the so-called, for some alpha greater than 0. I'm going to come back to you and tell you that not any alpha would work. You will see it soon. And what we do is this. We form a vector. That vector is this xj that we had. If you remember, let me just go back to, I think we were in this slide. This is what I call xj. I set this one up, come over here, and the way I'm setting it up is, if you go back to this, that's exactly how each element of that vector would look like, except for the first one, which is eta divided by 2. The rest is just eta. There is exactly the same, except is moving with the index. That means for x1 is nu 1, nu 1, nu 1, nu 1. For x2, I have nu 2, nu 2, nu 2, and nu 2, and the same would go to nu n. And do not forget that the nu was j minus 1 eta. That means the nu 1, for example, would become just simply 0, because when you substitute 1, nu 2 would become just eta, nu 3 would become 2 eta, and it goes on and on. Now, this is, as you see, is simply a model-free setup. The reason is once you have this characteristic function, you evaluate it at these arguments, and you're just forming this vector. Once you form this vector, the next step is this. You pass that vector through FFT routine. One more time, the FFT routine is you simply using the library saying Python, which is the FFT, you're calling FFT, you're passing this x vector, which was x1 to xn. The output is a vector y, which would look like y1 to yn. What you're doing is knowing that options prices would then be imaginary numbers. You pick the real part of them for each components. You multiply it by these, which goes with k1, k2 to kn, and that would give you the options prices for various different strikes. One more time, don't forget that the Km was nothing but beta plus m minus 1 lambda. You remember when we got lambda from for that constraint, which was 2 pi over n eta, and beta is you picking beta, which in the next lecture I would explain to you how to find beta. Now what I'm going to do is this. I'm going to, before we go to lecture 7, the last lecture on this series, I'm just going to actually go through 2 Python codes for you, which I'm explaining how to call FFT, but I'm going to do it 2 ways. One, I'm going to do it by simply writing it out. The one is by writing it out means an explicit implementation versus calling the Python FFT, and just show it to you that we would get exact same results. That means you can do the explicit implementation that nobody would actually do it. Everybody is typically calling it because that would become actually the efficiency of grabbing this FFT algorithm from the library, either in Python or in a language that you're using. Thank you. Hello. At the end of lecture 6, I mentioned that we are going to go through 2 Python codes. One is just simply a simple example, just simply explaining how to call FFT, but I want to do both calling the FFT from the library and also implementing explicit implementation on FFT, just to show it to you the results would be exactly the same. Now, here what I'm having is first, I'm going to import numB as MP. Then I'm just simply having an arbitrary vector of n by n. For our example, I'm using 8 by 1, which is, as you notice, is 2 to the power 3. For FFT to be efficient, it should always be 2 to the power of something, whatever that might be, 2, 3, 2, 4, or 2 to the power 10 or 14, whatever that might be. Then I'm having a complex vector. This is the vector, and it can be any vector, whatever vector you like. And simply I'm printing the elements of that vector, which is fine. Then what I'm doing is now I'm using the FFT algorithm. The FFT algorithm is simply in numB is numB FFT.FFT. You may say, why is 2 FFTs? Because you might use FFT or you might use inverse FFT. Then this part has to do with the FFT algorithms, and this part has to do with either you calling FFT or inverse FFT. I'm going to go actually through both of them. Now, as you remember in lecture 6, in one of the slides, I said you just simply passing x into FFT, getting y out. That's exactly what I'm doing, nothing more, nothing less. And I'm actually printing each element. This is y. Now, you might say, how about the explicit implementation? This is the explicit implementation of it. I'm literally going through the definition of FFT. If you remember in one of the slides, I had that definition, which was exponential minus I 2 pi over n, m minus 1, j minus 1 multiplied by x. Of course, here you don't see m minus 1, you see m. The reason is because I'm starting from 0 as opposed to 1. This is just simply the way I'm writing it. And then you say, what happens to the j minus 1? The j minus 1, I vectorize it. This is actually sitting here. I'm doing this just to speeding it up. And so then having 2 loops, I'm having 1 loop, and the other loop is being vectorized. For those of you who are familiar with Python, you know exactly what I mean. For those that are not familiar, just follow this, and you see actually this j is a vector. I'm sending it in. I'm taking advantage of this vectorization or vectorized operation that one can do in programming programs like Python and MATLAB. If that would have done in C++, I would have done it actually 2 loops. And let me do this, and then you will see the results would be exactly the same. This y is exactly the same as that y. Exact same results. One is because I'm just simply doing the explicit implementation of FFT according to its definition. Now, you might say, can I get x back? The answer is, of course, yes. If you remember, we said Anytime you're getting something from FFT, you want to get it back, you just simply do inverse FFT. That means what I would do is this. That's exactly the question I asked. Let me just go through it one and how to get the x back. Getting x back by calling x is equal to IFFT, which means inverse FFT. That means the y that you created, you got out of FFT, you put it back, you get x back. This is what I'm doing here, just in one line. As you see, that's the one-liner that I'm doing here. And this was the exact x that we started from. If you go on the top, you do remember that was the x that I had. As to be, I'm just doing a sanity check to make sure that you see anytime you do FFT, you always can get the original back by inverse FFT. Good. Now also what I'm doing is I am actually doing the explicit implementation, which is the definitions is in the explicit implementation. It is actually, instead of being minus, now is plus, because the FFT at the minus, the inverse has actually plus. And if I do this, you get exact same results back. You have this code, please go through it. I did this for just a sanity check for you to see the explicit implementation versus what you get from the library. They give you exact same results. The benefit of using the library is in the library, they actually using the technique that operations might, the explicit implementation, the operation would be on square, as opposed to what you get from the library is on log n. In the next Python code, actually, I'm going through how long it would take to run this, and then you will see the benefit of calling the FFT from the library. Thank you. Welcome back again. We are on, again, I'm going to go through another example of FFT, but this time, as opposed to having a vector of 8 by 1, I'm going to go to a vector with a much bigger size, which is 2 to the power 12. You would have the code, you can play with it. We already did the sanity check. I don't have to go through that. The only thing I'm doing here is, this time I want to measure the time that would take to run FFT, just to show you the benefit of it. The one that I'm using from the so-called the library versus the one that I'm actually doing it through explicit implementation. Here for the code, again, I'm using a NumPy, and as you notice, I'm importing time just to measure the time that it takes to run the operation. I'm doing here, it's just simply a random vector of size 2 to the power 12. The way I'm doing the random, there are many, many ways you can do it. I'm simply generating a random, a uniform random against NumPy. And as you notice, for the real part and imaginary part, I do it separately, and then I put them together. There are many different ways of doing it. This is just one way of doing it. Don't assume that that's the best way of doing it. Now, what I'm doing is, as you see, I'm going to send it through FFT, get y out. But before I send it, then I measure time. After I'm done, I'm again getting the time. And what I'm doing is, I'm subtracting the time from each other. As soon as before I go in, I call it the start time. When I'm coming out, I'm grabbing that time minus start time, and I would know my elapsed time, the so-called. Let's run this, see how long that would take. It's actually pretty fast. 5/10,000ths of a second is super fast. Let's do explicit implementation. Explicit implementation is very consistent to what we had from the previous Python code. And what I'm saying is, as you see here, explicit implementation, I just want to show you on square versus on log n. For this case, I'm again doing the vectorization. If you remember, we had this. And then I'm just going to go through this one with explicit implementation that I'm doing for FFT. If I run this, you'll see it took us half a second. It's, I don't have to tell you, it's 1,000 times faster. Let's do comparison between the y and y hat. They should be the same. I cannot show you all of them. I'm just picking maybe one element of each. That's exactly what I'm doing here. This is the element from the first one, the same element from the second one. As you see, they perfectly match. They perfectly match. They have to. That's just a quick sanity check for us to make sure that we get the same result. If you want to get X back, of course, you can call IFFT as well. My entire thing here is your appreciation of this time versus that time. That is why I would never ever recommend you to do explicit implementation of FFT. Just trust the library for FFT and inverse FFT. Thank you. Welcome to Option Pricing via Transform Techniques, Lecture 7. By now, you know why I call this Transform Techniques, because what we are doing is we're using Fourier transform for doing this. In this lecture, which is the last lecture, what I'm doing is now I'm going to go through options pricing via FFT. We already explained everything. But literally what I'm doing is I'm going through the implementation part, and then I'm going to price for 3 different processes. I'm going to price the options, option premiums, I would say, for different strikes, different maturities, but specifically for different parameters. Because if you remember, we discussed about eta, we discussed about n, capital N, which was 2 to the power n, and alpha. But you wonder how sensitive the options prices would be with respect to various different choices of eta, n, and alpha. That's what I'm actually trying to do here in this lecture. After I went through all the slides, what I would do is I would walk you through the Python code for this lecture and explain to you how actually I did that. Now, then let's do a recap of what we've done so far. What I would say is having the characteristic function of logarithmic of a stock price process. I keep saying this because my assumption is this is given to you. By no means you are going to sit down and drive this. Someone else, I'm assuming this is like a black box, exactly like an engine. You have the engine, you're just sitting down to drive the car. You don't have to be a mechanic to get to the engine. One can price a European. It's very important to mention this. One can price European. We're not talking about American options. These are the options that you have the right to exercise at maturity. No time in between. That's the difference between European and American. I want to make sure that we are clear here. Via FFT. And when I'm saying this, not only for one strike, that means for fixed maturity, as I said, you can do it for various different strikes. That's the benefit of actually using FFT. Now, again, I'm borrowing this from previous lecture, lecture 6. Having a characteristic function, we choose eta, want to make sure I emphasize, we choose n and beta. That means the user, who's ever using it, the trader, the risk manager, whoever using it, they have to choose eta, n, and beta. Of course, you can come up with some kind of a learning algorithm that would do it for you, and you will see as we go through the slides, it's easy to build these things. But at this point, I'm assuming the user is actually picking eta, n, and beta. And then as soon as you do this, then you calculate lambda from the constraint. You remember this, and the constraint was this constraint. That means once this and this gets picked, eta and n, you have to calculate lambda from that constraint. You setting nu up, you also set alpha, you form that vector. You remember this from lecture 6. I don't have to go through it. This is, again, I borrowed it from the previous lecture. You pass it through FFT, getting y out. By now you're comfortable with FFT. Not only I call it from the library, I did the explicit implementation. You have the code, you exactly know how that works. And once you get the y out, you just get the real part of it for each component or each entry, my apologies. You multiply by the corresponding damping here, which for, of course, the first one is K1, K2, and K3, and you remember Ks, and I'm gonna discuss beta soon. And that would give you a vector of n call options for those strikes. But maturity, don't forget, maturity is fixed at this point. Now, what will be the choice of beta? Going back again, beta is the very, very first strike, and then we set up when we set this one up, we go through this, and through these grid points, each of this is lambda. That means this would be your K1, K2, K3, to the last one, which is Kn. And it turns out the K1, the very first strike, would be exactly beta. That's how we design it. There are two common choices. Now, I'm gonna have this one here. I'm gonna discuss it, but I wanna make sure that for the quiz, I'm gonna set it up for you to make sure that you can convince yourself that I'm right. Now, if you want middle of a range corresponds to the at the money, that simply means the point that K is equal to S naught, then the way you would set up beta is the choice would be log of S naught, which is the spot price, minus N over 2 lambda. That means you know that you have N of these. This is the N. The N over 2 middle of the range comes over here. You want the middle range to coincide with the at the money. That means you want the K to be equal to S naught. Don't forget, I'm doing the log space because everything is a log strike space. That is why. That means this is actually what I'm doing here. Log of K in the middle to be equal to the spot. This is something that I want you to leave it as an exercise for you. Convince yourself that's the case. That's one case. The other case is if you want the very, very first call coming out of this. That means when you're looking at this vector, CTK1 to CTKN, the very first one you want to correspond to a specific strike K, you set beta to be log that K, a fixed K that you have in mind. Then these are the common choices. And you will see in the code as I'm going through it, I'm going with a second choice. I mean, there's no reason, just that's what I decide to do it. Now, for our case study, I'm going to assume the following parameter set. Spot of 100, a strike of 80, a specific strike. Do not forget, you may say you can get various different strikes. The answer is yes, but I just want to focus on one strike at this point. Risk-free rate of 5%, dividend rate of 1%, maturity of 1 year. Now, then I'm having 3 examples. The very first example is Black Merton Scholes. Now, I don't want to go through the stochastic differential equation. You may have seen it or not. I can simply go directly through the characteristic function, but I'm just writing it up. In a case of Black Merton Scholes, the assumption is that the stock price evolution follows the following stochastic differential equations, so-called what we call BMSSDE, which we're assuming that it follows the following one. As you know, this is what we call drift part. This is what we call diffusion. This is the volatility of the process. And this R minus Q, R interest rate, Q dividend. Now, for this process, its characteristic function, that means the characteristic function of the log of the stock price is given according to this equation. Again, this is an imaginary number. That's the spot, R, Q, sigma, maturity, sigma, T. And of course, this nu is this nu that I'm having over here. Now, in this example, I'm assuming for this example that sigma is 30%. Now, let me show you the table, and I go through the code that I use to populate this table. Then you have everything. You can do exactly what I've done here. Let's see what I've done here. I discuss N, eta, alpha, and beta. For beta, I already said I would do it to be log of K, which turns out to be log of 80 because I'm using it for a strike. Then this one is already gone. Then I have N, eta, and alpha. For alpha, I said alpha should be greater than 0. Greater than 0, strictly positive. then I can go from something very, very tiny to something relatively big, 10. And I'm going through this range. And you can pick whatever you like. You can go smaller than this if you wish. You can go larger than this if you wish. I can leave it to you. As a matter of fact, I can set up some either, maybe it would be good to leave it as a quiz or something like that. Anyway, for eta, I'm assuming two different choices. You can actually extend it if you wish, 0.1, 0.25. And for each of these, I assume one case n2 to the power 6, 1 2 to the power 10, 2 to the power 6, 2 to the power 10. That's exactly how I'm formulating it. I use these things and I populate this table. That means, for example, if you look at this one, that means for alpha 1, n2 to the power 6, and eta 0.1. That should be clear. If you look at the population, some of them you see I have it in yellow. In yellow means I already know that the true answer is this. How do I know it? Because for Black-Scholes, we have an analytical formula for it. Now, as you see, when you look at this table, it seems that some cases I'm a bit off. You may say, actually, I'm doing extremely well here. Why not? I'm going up to 4 digits. I don't have to. I could say up to a penny is good enough, but that should be fine. But as you see, for example, I'm pretty off here. I'm doing really, really badly here. That means, and I'm relatively off here too, but definitely alpha too small is not a good thing. For alpha too large, depending on what n is. But it seems that this range, I've done really well. And this range corresponds to something, actually I've done actually okay here as well. Then for alpha between 1 to 2, I'm doing well. That's as far as this. When it comes to eta, it depends on the choice of n. That means if the eta, for the case that, for example, eta is 0.25, no matter I'm using n 2 to the power 6 or n to the power 10, I'm doing still well. The reason is because the cutoff is far enough. But if you are at the smaller eta, for n too small, I'm doing a poor job. Then maybe what you should do, I didn't do it here, for you is using n.1, eta 0.1 and n2.8, which would become somewhere in between to see how well you do. I leave it up to you because, as you say, you have the code, you could simply sit down and do these things and convince yourself. Let's look at the next example. I'm moving from Black-Scholes to something like Hessian stochastic volatility model. Hessian stochastic volatility model, I'm having the SSD. The only reason I'm mentioning this because I had it for Black-Merton-Scholes. I want you to see this SSD2, SDE, my apologies. The only thing I want you to notice is if I replace this by sigma, this looks like exactly like Black-Scholes. But then it's not constant anymore. This itself follows another SDE. If you don't know about stochastic calculus or stochastic processes, that should not be any problem whatsoever. The only thing I want to emphasize is that unlike Black-Merton-Scholes, the volatility is stochastic. That means it follows another process itself. That's what I want to emphasize. And the only thing I'm saying here is this, that this is its characteristic function. The characteristics of log of the stock price is given by this. You may say, oh my God, this is very complex or convoluted. The answer is no, this is given to you. One more time, see what we have. We have the S0, R, Q, T, and you will see things sitting here or there. And of course, some cosine hyperbolic, some hyperbolic. You don't have to worry about this. The only thing is, it's given to you in closed form. And of course, I forgot to mention, there is a gamma here, which that gamma is nothing but this, which is, again, given to you. And for this example, this is a 5-parameter model. Let's make sure that we know what those are. It's kappa, theta, lambda, which you will see it. Sorry. This is kappa, theta, lambda. That's it. And there is a rho. The rho has to do with correlation between these two Brownian motions. That means we have two processes, one for the stock, one for the variance, and we're wondering if two are working independently or these two are correlated. If they are independent, This would be 0 because correlation is between 1 and -1. In this case, I'm assuming correlation is 70%, -70%. And the V0 has to do with the initial point that you are starting your variance. That means that's the initial variance. This is called the wall-of-wall, and that's has to be long-term reversion, and has to do with the speed of reversion. Anyway, one thing you have to know is this. Emphasizing one more time, my assumption is the characteristic function of the log of the stock price process is given to you and is a 5-parameter model. And for this 5-parameter model, I'm assuming that's the parameter set. Now, for this again, I will go and populate this table. Exact same table when it comes to alpha, eta, and choices for n. Let's look at the population. I already know the true solution is to this one, and it's easy to see because it nicely converges. One more time, it seems that this range still is a good range, roughly speaking, the alpha range between 1 and 2. But one thing you're noticing is it seems that to get there, still I'm relatively doing well. I'm off by a penny, but not here though, not here though. One more time, if you remember, we had this in earlier as well. When eta is small, you have to make sure that you compensate on n. Maybe then you should try 2 to the power 8. I'm leaving this to you. You have the code, you can play with the code, you can convince yourself to see what the good choice would be. But it seems that this is a good range for alpha. Anything between 1 and 2 should be good. Small is not good. When it's large, still you're doing okay. I mean, you're doing well, but then if you try 50 or 100, you will see actually that would then be a good choice. Now, and when it comes to, let me see, when it comes to eta, seems that eta 0.2, 2.5 with 2 to the power 10 for n, you would do a good job, which is consistent exactly with the previous case for Bragg-Merton-Scholz we had. Let me go through the last model is called variance gamma model. I'm not going to go through this ST because it's a bit more complex. I'm having it over here. The only thing I want you to notice is what's interesting about a model like variance gamma model is actually, as opposed to diffusion, this model is what we call pure jump process. Without actually going through the formula, I can tell you the difference between the two. Pure jump process, a pure jump process or pure jump processes are processes that the stock can actually jump, or the stock prices, it could jump, as opposed to diffusion processes that it has to go like in, how should I say, is diffusing, and you can actually have jump in them. But here is pure jump. That means you can have really, really big jumps, which would make it more realistic. And these classes of models, variance gamma or any variation of those processes, actually would give you a more realistic way of trying to capture the behavior of the stock market. Now, for this process, the characteristic function is given by this formula. One more time, again, we have the S0, R, Q, T, and the parameters of this process, which are sigma, nu, and theta, sigma, nu, and theta. I intentionally called the nu here, and I call this u for you not to get confused, because if you remember, we always use, unfortunately, we always abuse some of these notations. I'm using nu for the parameter of the model and using u now here. This u is dummy anyway. You can call it whatever you like, whatever you like. Now, this is a 3-parameter model, the sigma, nu, and theta. Sigma, again, is volatility. Nu is what I would call kurtosis. And theta is what I call skewness. That means what the system says, it would allow you to have both kurtosis and skewness. Now, the interesting thing is, if you set these two equal to 0, you get Black-Merton-Scholes back. That simply means there is a built-in function to variance gamma. If there is no jump in the market, which simply means I get rid of these two, you would go back to Black-Merton-Scholes, which makes it very realistic, actually. At some point, actually, in next lectures in other series, I'm actually going to walk you through this and seeing that if you introduce some prices, which they're coming from Black-Merton-Scholes, variance gamma can detect the fact that they're coming from Black-Merton-Scholes. That means if you calibrate it, you would get these two almost 0, and then the only non-zero would become the volatility. Anyway, said enough here. Let's go to the table. That's the table exactly like before. Premiums for various values of alpha, n, and eta. Again, exact same series for alpha, for eta, and for n as well. One more time is up to you. I did it 2 to the 6 to 2 to the 10 for n, but maybe I should have had 2 to the power 8. I leave it to you for you to do it. One more time, you're seeing this range is a good range. Actually, you can go even further, but I want to be more consistent with other cases. Alpha between 1 and 2. And it seems that for eta 2.5 and n being 2 to the power 10, you're doing a very good job. And I know this solution is this, which I'm having it in yellow boxes. Good. Let me go through all findings and observations that we are having here. Now, findings and observations, just try to wrap this. The pros and cons of using transform techniques for options pricing. Now, the very first thing would come in mind is a model-free setup. What do I mean by this is you have an engine, like almost a black box type. You sending this in plus some parameters, and this FFT engine, the options pricing via FFT, let's call it option pricing via FFT, you get prices out. It's a free setup. That means you're just sending this in with the parameter set. Done. Now, it is fast. What I mean by it is fast is that for n different strikes, you can get n different prices with the order of operation O n log n. I'm emphasizing again, this is as opposed to O n squared. This is a huge plus, huge plus. Now, what are the cons? One, the very first thing will come in mind is the constraint on lambda. Because of this constraint, you have to be careful to make sure that the spacing do not become too wide. That means you can't just go and pick any eta or any n. You need to be always aware of, you pick eta and n in such a way that lambda wouldn't be too big. Also, the choice of eta, n, and alpha, you need to be careful with it. All of these things that I did for you, we came up with a conclusion. This is relatively speaking good, n maybe 2 to the power 10, and eta something like 0.25. Having said this, how would you know that if I give you a different process that would work for it? That means you should always be available of some optimal choice for eta, n, and alpha for those three processes: Black-Merton-Scholes, Heston stochastic vol, and variance gamma. We already showed it to you, but what happens if I move to some other process? Then you need to always do a bit of, I don't call it, maybe scenario analysis to make sure that actually you are picking a good choice for eta, n, and alpha. This is as far as what we have. What I'm going to do is I'm going to go through the Python code, the implementation of this options pricing, and then simply show you how to price it using FFT. Thank you. Hello, as I mentioned at the end of lecture 7, we have a Python code that's simply all the tables that I populated I use this code, which you would have it. You can play with it. And I just want to walk you very quickly through the code and then run maybe a few cases. Now, as usual, I'm using I'm importing some libraries. I'm using NumPy, CMath for complex math, and time for just in case of trying to measure time. You might notice actually I'm importing warnings because sometimes we get certain warnings. I just simply want to ignore those warnings. If you want to see the warnings, just comment it out. But I'm having it just to make sure that the warnings wouldn't show up. The parameters, the so-called fixed parameters, I'm having a spot of 100, a strike of 80. I said one specific strike if you remember, but I'm working with the log of it. That's why I'm doing the log of that. Interest rate of 5%, dividend of 1%. The parameters that I'm using for FFT, of course, you can use any n you want. I'm just going to run it for the case as n 2 to the power 12. That's what I'm having here. A step size for eta, I'm having 0.25, and alpha, I'm using 1.5. I mean, as I said, you can play with this in the population. Actually, I was populating the table. I use various different values for these things. Now, let me just run this. Shift Enter. A step size in log strike space. Don't forget, if you remember, I said lambda, the constraint would force you to do 2 pi over n eta. That's what I'm having over here, which is the step size in the log strike space. And choice of beta, there were 2 choices. As you see, I'm having both here, but I commented the first one. I'm using the second one, which is setting beta to be log of that k. The model under consideration that I'm using is Heston. I'm using Heston. And as you notice, for each of these, depending on the model of the choice, I'm setting the parameters. For GBM, there is 1 parameter. For VG, there were 3 parameters. For Heston, there are 5 parameters. Then depending on which model you pick, it would go and choose from these choices. Now, the generic CF, which is the generic characteristic function, depending on the model, it would create the characteristic function for you. As I said, it's a model-free setup. That means you pick the model and it would go and generate this characteristic function. These characteristic functions that you see here that I've been implementing it comes exactly from the slides, that we had in lecture 7, implementation of that. The only thing you may notice is in case of VG, if nu is equal to 0 is a different implementation. You have to be careful with this because for nu 0, it would become, you would go into some undefinedness that you need to use L'Hopital rule for it. That's why I already did this. I will leave this one as an exercise for you. I just want to make sure that you understand that case that nu is equal to 0, you need to take care of analytically. You may say that, do I run to nu equal to 0? Typically, you can make it something tiny positive. You don't run into it, but in case if it becomes 0, that should be fine. Now, if you do remember, in the end of lecture 5, my apologies, lecture 6, I said if you're interested in just 1 strike at a time, no need, as I'm writing here, no need for fast Fourier transform. You can just do the evaluate the integral, which is exact implementation of what we had at the end of lecture 5. End of lecture 5, he said, if you have 1 strike, there is no need to go any further, no further step. But if you want to do more than 1 strikes, then you need to use this efficiency of FFT. Then in case that you just want to do 1 strike, you can just use this evaluate integral. In case of having more than 1, then I have this generic FFT, which is exact implementation of setting up x, the x vector. When you set up the x vector, you send it through FFT. When you get that one back, you get the real part of this, as you see. And when you get real part, you multiply by that multiplier. That's exact implementation of exactly what I had in the slides. Setting up the x vector, which that's this part, and then you getting the x vector out, you passing it through the FFT. Once you get y out, you get the real part of it, and then you do that damping. That's exact implementation. You have the code, you can go through it. The only thing I would say about it is sometimes I try to take advantage of this vectorization, which I'm not sure I did here or not, but you can go through the code and you will see it. Let me just run this one. I do that, Shift Enter. And now what I would do is, I'm emphasizing what the model is. I'm getting the F50, calling the F50, passing those, and knowing that the choice of the beta, the first entry coming out of here, that first entry would be what I'm interested in. Let's run this. Now look what I've done here. What I've done here is this. I intentionally ran both the one, because I'm doing one strike. I'm running both the one that I'm using F50 and the one that I'm just calling the evaluate integral and comparing it against each other. Then option via F50 for strike 80, the option premium is this. The execution time was this. Now I'm saying option via integration. Well, option via integration for strike 80, I'm getting exact same, has to be. And it turns out actually the time is slightly actually longer. The reason for it is because I'm doing the implicit, my apologies, explicit implementation. Then you still better off using FFT here. And as you see, the results would be exactly the same no matter what. But then FFT is much faster to use. You have the code, you can play with the code yourself and make sure that, as I mentioned, make sure that in lecture 7, make sure you go through various different values of n, alpha, eta, and then play with it yourself to convince yourself what would be the optimal choices for those three. Now, what I will do in the next 7 lectures, which would be on model calibration, what I'm trying to do is I'm trying to use this engine as an engine for pricing and go to the market. Let's say I go and look at the option on Apple stock and then trying to see if I can find a parameter set, say for Houston, for example, that I can capture by plugging it into Houston, create a surface coming from Houston, and that surface would be closely matched with the option surface comes from the Apple stock, Apple company stock. And this process of doing this kind of reverse engineering is what I would call calibration. I have 7 lectures on model calibration that I walk you through that one in my next lectures. Thank you so much. We wrapped up in the first series, we wrapped up our lectures on options pricing. Now in the continuation, we will be discussing model calibration. We will be having 7 lectures on that. And I'm gonna start by just do a quick recap of what we already covered on option pricing modules. What we did was we came up with a generic options pricing model. And the way it worked was we said we pick a model. We discuss few models like geometric Brownian motion, Houston, variance gamma. Then pick a model, pick a parameter set for that model. Theta, for example, for geometric Brownian motion, that would be just sigma. If you have Houston, then for Houston it would be a 5-parameter model, kappa, theta, lambda, rho, and v naught. And if you have Vg, it would be sigma, nu, and theta. Of course, we can have more than that, but we just decided to discuss GBM, Houston, and variance gamma, Vg. For your homework assignments, I may actually decide to come up with some more models for you just to get used to other models as well. Then for a fixed maturity, what that module that we developed would give us the call options prices for a range of strikes. When I'm saying a call, of course, we can do it for a put. We need to make some changes to it that I'm going to assign it actually for your assignments. A notation for model price would be, we typically for model price, we're showing it as V hat. The reason I'm calling a hat, just showing that is a model price, is not the market price, then definitely we're having the spot, a strike, risk-free rate, dividend rate, and maturity, and the parameter set. I put a semicolon here just to show that the first set of parameters, they're known parameters, the contractual parameters. This one is a parameter set that actually, depending on the model, you may have various different parameters for that. And I'm emphasizing again here that the theta is a parameter set. Now, for market prices, we discussed already the model prices. For market prices, like any price, for options prices, there are bid and ask prices as well. Now, if you are buying, you get the ask price. If you're selling, you get the bid price. Do not assume a buyer would get the bid price. No, there are bid and there are ask prices in the market. If you're buying, you get the ask price. If you're selling, you get the bid price. And definitely it makes sense that when there are more buyers than sellers, market would go up, and vice versa. That means when there are more sellers than buyers, you will see the prices would go down. Now, when it comes to bid and ask, it depends on exactly the type of the options we are working on. For example, if you are working with large trading volumes or the so-called liquid option contracts, bid and ask are typically very tight. On the other hand, when we don't see that much volume or the so-called illiquid options, then we'll see that the bid and ask are wider. To see this, the best thing I decided to do was I decided to go to Bloomberg. I picked, for example, the Apple computer, and I decided, the Apple company. And I decided to show you the options prices for Apple stock. I'm having actually 4 slides on that. That was the snapshot that I'm getting on July 23rd of 2018. I'm going from the shortest maturity to the longest maturities. There were 9 of them, but I'm not showing you all. I'm just giving you a snapshot of those prices. And I decided to put all of those into Excel sheet that I'm providing it to you. And for the next 7 modules, actually, I will be just working on these prices. A couple of things to notice here is, for example, we see the calls and the puts. On this side, on the left-hand side, we've seen the calls. On the right-hand side, we are seeing the puts. For maturity, the shortest maturity here, which was on August 17, 2018, we are seeing various different strikes going from 170 coming to 210. And as I mentioned earlier, we see bid and ask. You'll see the bids are sitting on this side, the asks are sitting on the other side, and it's relatively tight. For example, for a strike of 182, we see the bid and ask just being about 10 cents, and the volume are sitting here. Some volumes are larger than the others. Now, that's a snapshot that at the time that I was taking the options on options on Apple stock. Now, I'm going a bit to a longer maturity, slightly longer from August. I'm moving to September 21st, 2018, exact same scenario, bids and ask, and you see the volume. This has, for example, the highest volume and very, very low volume here. On a lower volume, as you see, the bid and ask is a bit wider than the higher volume. No question about this. This is exactly what I mentioned earlier. Depending on the volume, typically the bid and ask gets tighter or gets wider. Now, one thing to notice is for equity options, they always expire on Friday. If you go and look at these dates, for example, September 21st, 2018, you will see this actually is a Friday. We go to longer maturities. The longer maturity, for example, here I'm having January 17th, 2020, which is with respect to July 23rd, 2018, is relatively long, is more than a year and a half roughly. And for that one, you see very low volume, and the bid and ask are much wider. And the longest maturity than on Apple that I can at least find on Bloomberg, it goes to June 19th, 2020, almost 2-year maturity. And for that one, again, very, very low volume. Actually, some volume doesn't actually exist as much and is much wider, like $2.85. Then it's just for you to give you some insight into exactly what you would see in the market when it comes to bid and ask on options prices. Typically, when we're working with options, typically we work with the so-called mid price, which is the average between bid and ask, divided by 2. Some people like to make this one volume adjusted. At this point, we're not getting into details of that. For the assignments, I will ask you actually to play with some of these. At this point, I'm not actually getting into it. Now, what I'm showing here to you is I'm actually plot the entire surface for all maturities and all strikes, and just simply showing you the so-called call price surface. I'm going to switch to the Python code. That what I'm doing is I first reading the Excel sheet that I have all the prices and I'm grabbing from Bloomberg. I'm simply reading it. You need to do a bit of formatting, but you have the code. You can go through the code and see how it works, and then simply plotting it. And when I'm plotting, I want to make sure that I put it in a matrix form. That means simply, if I'm writing it as CKT, C for the call, then the K would be the strike or strikes. That would become so-called maturity. And having the surface, that means if anything is missing here, I'm kind of doing interpolation to make sure that I have the surface for every strike and every maturity, because they not necessarily they would align. Then in that regard, if you look at the code as I'm going to go through it, you'll see that to make it for every strike and every maturity, I do interpolation just to set it up to be able to plot the surface. For the surface, as you see, I'm showing it in days for maturity. It goes from very short day to much longer day, roughly 2 years. Strikes goes from 170 to 210. And then on this side, vertically, you will see the call prices. Goes from very short maturity to higher maturity. And as you see, fixed maturity, as the strike increases, the prices would go down. And this is consistent through every maturity. Then I'm just going to switch to the Python code and actually show you the process that I explained. Reading the Excel sheet and then simply plotting it. Here is the sample code that I'm having for plotting the surface for the option on Apple stock. I'm actually calling that Excel sheet, I'm calling it data_Apple XLSX. And what I'm doing is I'm simply reading it. And Python already has the so-called, we are using the pandas library to read the Excel. Is actually, in that regard, Python is pretty powerful. We're simply reading it. And as I said, we have the bid and the ask. And what I'm doing for the mid, I'm simply doing the average. I'm using the mean, sorry. You can show some of the data, is up to you how you want to show it. But as I mentioned earlier, I'm making a mesh for the strike range and maturity range. For the strike, by eyeballing, you see it goes from 170 to 210. For maturity, I'm just going through all and I'm picking the unique days for maturity. That's what I'm doing. I'm putting everything in a matrix, DF calls, and simply setting up the grid. From a vector, I'm going to a grid for both the strikes and maturity. And simply what I'm doing as I'm reading, I'm just simply populating that matrix. Nothing more, nothing less. And for plotting the surface, I'm using a 3D subplot in Python and simply plotting the surface. And let me just run this one. Shift enter, shift enter, and here shift enter. That's exactly how I'm doing this. One more thing just to remember, as I mentioned it earlier, for cases that I do not have the strike, I do, as I mentioned earlier, I do interpolation. That means for every maturity, if the strike does not exist, I do interpolation to make sure that I can populate the matrix for every maturity I have the corresponding strikes. That's as far as this. Then in the next module, what we're doing is we will be using the so-called these call prices as the so-called market prices, and then we show exactly what we're trying to do with these market prices, finding a model that we can do a nice fit to those market prices. This is the model calibration lecture 2. In the previous lecture, what we did was the very last part of it, we plotted the 3D surface for the option surface for the Apple stock, and this is actually the this is a snapshot of it. I'm exactly borrowing this from the previous lecture. Now, before we get into calibration, I just want to go through some the so-called questions and answer. I'm coming up with 3 of them. There could be much more. The very first thing is there a model can explain the entire surface? Now, I would say in general, finding a model to fit the surface perfectly is impossible. Having said this, one can always find a model that you could do a decent job. This is important. When I'm saying a decent job or a decent fit, that means what's acceptable to us or to you. I mean, what do you think that would be a good fit? Is that tight enough? Is that acceptable? Is that within the so-called bid and ask in the market? This is actually the essence of calibration. If somebody asks you what exactly that calibration is, you're saying that we're trying to find a model to do a good job. As this, I'm kind of jumping. I haven't defined what exact calibration means. Now, the next question is, if you want to find a price at the maturity which is beyond the available maturity. For example, for Apple, the maturity was the longest was 2 years. Now, how about if you want to find it for going out to 3 years? What would be the price for that? Let's say you want to buy or you want to sell at a 3-year maturity. Now, the whole idea is market doesn't exist for it. Maybe you want to offer it, you want to bid, or something of that form. Then the question is, what you will do is, you say, I can do extrapolation. That means I have a bunch of them, let's say something like this, and then I can extrapolate to go to 3 years. This is 2, I can go to 3. Now, when it comes to extrapolation, you may call it model-based, you may call it curve-based. Curve-based means simply you fit a curve and you extend it. Some people don't like the idea. They say there is nothing behind it. The model-based is actually what I will be focusing on. Now, the last question I will be asking is, if shorter maturities move, does it impact longer maturities and vice versa? The answer is definitely yes, but by how much? Not easy to answer. Definitely if part of the curve moves, it would impact the other, but by how much? That's something that actually is not easy to answer, but sometimes you're seeing that if the shorter maturities start moving, how does it impact the longer maturities? Is that possible to somehow come up with a way to know it? That's the essence behind kind of quantitative trading that people are trying to understand and trying to act by looking at these moves. Now, it's time to actually come up with a definition for calibration. The way I'm defining it is the process of adjusting a parameter of a model, the parameter set of a model, or the parameters of the model, such that what you're seeing in the market and what comes out of the model would kind of closely match, or they would be compatible, or they would be close enough. This process is called calibration. That means you have market prices. Again, I'm maybe jumping a bit. We already had this. You have model prices, you have market prices. Of course, this is not changing, this is fixed, but you can change this by tweaking theta. Now you try to tweak it in a way that these two gets close enough, roughly speaking. Now, the simplest one can imagine is when you have one price and one parameter. And the best example of it is implied volatility. You're trying to find a volatility such that for the same strike and maturity, model price matches the market price. As I said, one price versus one parameter. And this is what for that case, that would be volatility, actually is implied vol, which people write it like this. Sigma implied. A market convention for that is Black-Merton-Scholes model. That means in Black-Merton-Scholes, which is just a one parameter model, or GBM, I said that if you remember earlier, it's just one parameter model, just one parameter, just sigma. And what we're trying to do is we're trying to find sigma, which for the given price in the market, the model price would match the market price. What I've done is this. I'm going to go through this code. I have a simple Python code, and what I did is I'm starting from a very, very small volatility, very, very tiny vol, go to relatively higher vol. The higher vol is on this side is 40%. The lower one is 1%, and I'm coming from 1% to 40% and seeing where the model price would match the market price, and it turns out to be at 21%. As you see, I'm looking for the Apple, the strike of 185, maturity of 151 days. The price was 13.75 if you go back to the Excel sheet, which I'm going to show it to you actually. And I'm going from a small vol, very tiny vol, to a higher vol. Of course, you may say, why 40%? Why not higher? I already kind of knew in advance, but you can just push it, go higher. And I'm seeing which one corresponds to that 13.75, and I find that 21%, if you substitute 21% into Black-Merton-Scholes formula, its price would be the same as 13.75. And that is what we call implied vol. Now I'm going to actually do this by going through the code. Now I'm having now for the figure that I showed it to you on implied vol, I'm going to actually walk you through the code and show you actually how you would do this. This is just simply just importing some of the modules. I'm having the read plot option surface as one of the modules, exactly the code that I ran earlier. And then I have modules for calibration, which I call it MFC. The modules for calibration are the one that we have the options pricing in it. Later on, I would go through it and you will see, but whatever I did in the lectures on options pricing, I put it into the modules for calibration. That's exact same engine, no difference whatsoever. And I call it as MFC in short. Now, of course, and I'm also importing some of the plotting tools. Now, the model under consideration is GBM. That's simply the plot, surface plot. Now I'm grabbing for maturity 151 days and a strike 185. The call price is 13.75. Look how I'm doing it. I already have the surface. Then I'm picking strike and a maturity and corresponding options price. This is completely, I mean, I decided to go pick on the maturity the fifth element. Remember, it starts from 0, and then for a strike, I'm doing the seventh one, and the corresponding one would be on a call surface, the one that corresponds to 4 and 6, because I have the option surface, and I'm just simply showing it over here. You may wonder what's the difference between T days and T. T days would be in days for maturity, and a T would be the one in years, which I'm doing it up there. This is just when we are pricing, we have to have maturity in years, not in days. That's just simply what I'm doing with the division by 365. Now, having this, what I'm doing is, as I said, I'm going from a very tiny vol to relatively a bigger one, and I'm doing it in a step which is 0.5%. Then I'm starting from 1% to 40%, a step of 0.5%. And don't forget, this is the way I'm doing it through my range. If you remember, we had this my range before, but it's part of the modules for calibration. And what I'm doing here actually is just for illustrative purposes. This is actually not the most efficient way of doing this. There are much more efficient ways of doing it. But I just want to explain to you that if you have just one parameter and you want to do actually this, the so-called reverse engineering or calibration, in this case, simply what you're doing is you go from a very tiny one to a long one. You keep doing it until your model price and market price would match. That's exactly what I'm doing here. And for pricing, I'm using the generic FFT module that we went through it during the options pricing lectures. And simply, as I said, is a black box to us. You simply put in the parameter of the model, spot, strike, interest rate, dividend rate, maturity, alpha, eta, n, and model. You remember we went through it. No matter what model you have, this is the beauty of this. This call does not change. The only thing is you change the model and you change the parameter. If you come over here, you see the model, I call it GBM, and then the rest of them is the parameters. Of course, for this case, the parameter is just one parameter, and I'm sending it in like this, as simple as that. Now, when I'm grabbing KM and CT underscore KM, I'm grabbing bunch of strikes and the corresponding calls, but it's been designed in a way that the very, very first entry, which corresponds to 0, happens to be the one for that specific strike. That's as far as it. And I call it C hat. The hat means this is the so-called the model price. And I'm comparing the model price with the market price, which, as you see, the market price, I call it to be C here, and is not changing. The model price changes as I'm changing sigma, its parameter. And as I'm going through this loop, I'm looking at the difference in absolute value between that C hat and C, the one that gives me the smallest possible difference. It has to be 0, but let's say very, very close to 0. This is what I call to be my implied vol. And as you notice, I first start with some error which is relatively big. And the minute that I see my error is less than that big one, this becomes my new one, and the corresponding one becomes implied vol. As I'm doing this through the range of the so-called vol, I know which one exactly would give me the implied volatility. If I run this, it's running now. It was 21%. That's exactly what's the so-called implied volatility. Now the plot, simply what I did was for each of these, let me explain what I mean by each of these. For every sigma, I have corresponding call, and I'm putting it into an array. As you see it, I'm putting in a sigma array and C array, and I'm just plotting it over here. And then that way I can see exactly how vol changes, the call prices changes with different vols, and I know exactly the one that corresponds to the one that I'm looking for, which is 13.75. One more time, this is not the most efficient way of doing it. This is for illustrative purposes, but as we get into model calibration for models with parameter more than just one parameter, actually we'll see that that helps us to understand how to do the so-called discrete search, or a way of finding the optimal parameter set. Thank you. Hi, this is the third lecture on model calibration. We are just following what we did in the first two lectures. Just a quick recap that in the first lecture we just simply discussed the options prices, bid and ask on options prices. We also plotted the option surface on the actually options on Apple stock, Apple the company. And in the second lecture, actually what we did was we simply actually showed that for each point on that surface, we can find the so-called implied volatility, the volatility that if you substitute into Black-Merton-Scholes, it would match with the model price, and the market price would match. But now we are going to actually move on and try to do calibration on the entire surface or part of the surface. And for that, we are going to actually go over the formulation for calibration. And for that one, we are going to start from notations, which we're going to kind of revisit what we did in the first two lectures. Now, on notations, the way actually I'm doing it is I'm always looking at the market price as the so-called the spot today, strike price, risk-free, dividend rate, and maturity. And as you noticed last time, we have a bunch of strikes and bunch of maturities. Now this is just for one of that pair of strike and maturity. For the model price, it looks exactly the same, except for the fact that I'm putting a hat, just simply showing that it's not the market price, it's actually the model price. And here I'm having theta, which has to do the parameter set for the model. Depending on the model you have, it might be for Black-Merton-Scholes, just one more time repeating myself, it might be just one parameter, which is just sigma. But if you have Heston, which is a 5-parameter model, you are going to have kappa, theta, lambda, rho, and v naught. And I'm putting semicolon because I want to make sure that you know these first 5 are what's known in the market. That's why we're seeing it up here as well. But when it comes to the theta, it depends on the model. And of course, there could be various different parameter, starting parameter sets that we are having that we will be discussing that as well. I'm just emphasizing again, theta is the model parameter set. Now, in short, because that's a bit too long, in short, the way we're calling it for each pair of strike and maturity, we just simply putting it I. And then to distinguish this with model, we just have the hat and the theta, just to make sure that we're having VI versus VI hat theta, market versus model. Now, formulation, I'm writing it as this minimization. Let's make sure that we know exactly what we are talking about here. Assuming we have n instruments, then I goes from 1 to n. Then is the number of instruments, or the number of the prices that actually we're having in mind, we're seeing in the market. Then we have n of these, n of these, and of course, corresponding for model prices, we have exact n of that as well. H is an objective function. We sometimes call it objective, sometimes we call it cost, sometimes we call it error. They're all exactly the same. It's an objective function that we are applying to discrepancy, the difference between these two. And O, that we are having it here, is the space for all possible parameter sets. By all possible parameter sets, what I'm saying is this. For example, if you're having Black-Merton-Scholes, let's say 1 to make it simple, then sigma is definitely has to be positive. then starts from 0, something greater than 0, less than, say, infinity. Of course, infinity, in a way, we never have volatility of infinity, but let's say something like that. That would be the so-called O for us. Then O would be the space from 0 to infinity for all possible value that we can have for sigma. You can imagine if you go to something like Hessian, which is 5-parameter model, then you have to consider the range for each of those parameters actually in the parameter set. I'm going to come back to this actually. Now, the possible forms, the few formulations, it could be, in a sense, on an absolute difference to the power p, which p is greater or equal to 1, any p greater or equal to 1. And don't forget we have absolute value here, because if it's 1, it wouldn't make sense not having absolute value. Now, it could be applying to the relative error, or it could be applying to the log difference. These are various different formulations that you might have. Now, but the most common one actually is what is called weighted least squares formulation, which simply would be, as you see, we are trying to minimize. This is the squares, would be least squares because we're minimizing the squares, but this is the weighted one. You might wonder what those weights would be. There are many different possibilities for it. One common one would be, for example, the inverse of bid minus ask. As we discussed in the first lecture, we have bid and ask spread, and you may actually come up with a weight that is reverse of bid ask, or some other cases it would be volume related or volume adjusted or things like that. I'm not going to actually focus on this at this point, but for the exercise problems, actually I may give you exactly what I will be covering in the next few lectures and just ask you to make it weighted least squares as opposed to just simply least squares. That's something that you will be working in your assignment. Now, in the parameter setting, what we are saying is we are saying that let's assume n sub I would be the number of calibration instruments. For example, for the Apple stock, as you will open the Excel sheet that would be posted for you, see you have more than 300 instrument calls and puts, 300 of them. Then NI is about 300. And let's assume NP, N sub P, be the actually the number of model parameters. For example, for Black-Merton-Scholes, this is 1. For Hessian, actually, this is 5. Now, it's possible there are 3 different scenarios for it. First scenario is these two would be exactly the same. That means the number of instruments, calibration instruments that we're using for calibration would be the same as the number of parameters in the model. An example of this case would be actually the implied volatility. For the Black-Merton-Scholes, we have one parameter, namely sigma, and let's assume just one call or one put price. Then as you see, we have just one instrument and one parameter in our for our model. That's an example of an example that NI would be equal to NP. The second case would be the case that the number of instruments is greater than the number of model parameters. This is what we call underparameterized. And the third case is actually reverse of that. The number of instruments would be less, which we call it overparameterized. This is typically not the case. We typically don't see this in the market. We never develop a model which the number of parameters in that model is more than what we observe in the market. This is not typically, I haven't seen it myself. But let's assume this is out. Then the most common case is actually the second case, that the number of instruments are typically much bigger than the number of parameters in the model. That's typically the case. Having said this, it does not guarantee that there would be a unique set of parameters for that model. That means depending on the objective function, depending where you start, which I'm going to focus on this shortly, you may actually end up finding a different optimal parameter set. That's actually would be my focus for the next few lectures. Having said this, the second case is the most common one, and depending on how you set things up, you may get actually different result. Now that's the last slide would be very suitable for exactly what we were saying. Then when it comes to the so-called recipe for calibration, the specification of a data set, which simply means how much data you will be using. Maybe you have roughly 300 instruments, but are you going to use all of them? Maybe use part of them, maybe use just call, maybe use just put, maybe use out of the money calls or out of the money puts. There are various different specification that you may have for your data set. The choice of a model. Now, nobody's telling you that, for example, the market is following something like Heston or following something like variance gamma. Then is your choice which model you think would be suitable for that market. Then the choice of a model itself makes a different fit, and depending on exactly what kind of a model you're using, you may be doing a good fit to one side and you're missing the other side. It all depends. As I said, it depends on exactly what your emphasis would be on. The choice of the objective function or the cost function. You remember when we were discussing the cost function, the objective functions, we said there are various different formulations for it. We said weighted least squares would be the most common one. Having even said this, for the weights, there are various different ways that you can set up the weights. You may actually have the weights all equal to 1. You may actually have the weights which are the reverse of bed and ask. You may have the weights which are proportional to the volume and the like. The choice of initial parameter set. When you're having a parameter set like in the Heston case, like kappa, theta, lambda, rho, and v naught, then as you see 5 parameters, and kappa could go from, say, something from kappa supposedly is going to be positive. This is supposed to be positive, positive. Rho would be between 1 and -1 because that's correlation, and v naught again supposed to be positive. But when I'm saying positive, positive means kappa is something like 0.1 or kappa is 10. Are you going to start from kappa is small or kappa large? The same thing for theta, the same thing for lambda. When it comes to rho, are you going to have it close to -1 or close to +1? And the same scenario would go to v naught. Then the choice of initial parameter set is important. At the end of all of that, when you do all your formulation, which you have your formulation, which is some kind of minimization, what optimization routine would you pick for this? The optimization routine could be gradient free, could be gradient based, there could be something which we call the so-called brute force, and the like. That's something that actually I would be working on it in the next lecture. Thank you. Hello, this is Model Calibration Lecture 4. In Lecture 3, we actually finished by going over the recipe for calibration. I'm borrowing the last slide from the previous lecture, and I'm starting from that slide, which was the recipe for calibration. And what I will be doing, I will be actually delving in each of these actually items. I'm not saying these are the entire items. They could be some more, but these 5 to me are the most important ones. We discussed the first thing was a specification of a data set, choice of a model, choice of the objective function, cost function, choice of the initial parameter set, and what optimization routine one would be used for our calibration. Now, when it comes to a specification of a data set, I think I mentioned this, I'm just repeating it and emphasizing more. You may use all available prices. Again, going back to the Apple example, because I'm providing you the spreadsheet and you have all the calls and puts for the day actually are retrieved from Bloomberg. We had roughly about 300 instruments. And you wonder, would you use all 300 of them, or you use those with higher volume or more liquid ones, or you use those which are out of the money for calls and puts? Or in cases, there might be something that the trader, the user, may come up with his or her own way, that you may want to emphasize on shorter maturities more, or sometimes on longer maturities. As you're seeing, there are various different ways one would be looking at these things. Now, on the choice of the model, there are various different models. For this Apple case, for this Apple example, I'm actually will be working with Heston stochastic wall to fit part of the surface. You can use, as I said, the entire or part of the surface. And when I'm saying part of the surface, for that example, I will be using mostly call options. Don't ask me why not put. I'm actually, for the exercise, I will mix it for you to use both calls and puts. At this point, I'm just focusing on calls. And one more time, for Heston is a 5-parameter model, and we are trying to find the best parameter set such that the part of surface that I'm using, the so-called market prices and model prices would match very closely. Now, the objective function. It is what I call root mean square error, or what is called actually, is exactly like the weighted least squares, except the weights are set to be 1. And when I'm saying root mean square error, as you see, this is the square part divided by the number of instruments and the square root. And that makes it root mean square error. You could have just simply did it like this, and that would not have any difference whatsoever when it comes to calibration. Having said this, when you do root mean square error, you have a sense when you're looking at the number, because that number exactly would be in cents, or say in dollars, as opposed to a number that you don't have any sense of it, because you're looking at the root mean square, and that means it would be in dollars. Now, the choice of initial parameter set. We already discussed about the cost function. We already discussed about the what part of, when it comes to a data set, what data set we'll be using. The third one was actually the choice of initial parameter set. I'm asking few questions here which are very, very important actually. Question 1, how important is it to start from a good starting point? It is very, very important. Why? Because I'm actually exaggerating here. Let's assume the surface looks like this. Let's assume this is the surface. This is the error function that you're having. And let's say this is your global minimum. Now, if you start here versus if you start here would make a huge difference. One reason is because this region is flat, and optimization actually may get stuck here. But if you start over here, you see very quickly you're coming to this point. Then a good starting point is very, very important. That's the first question. The second question, how to find a good starting point. I'm going to show it to you how, but in general, it's not an easy task. Actually, it could be very challenging. Depending on the model you have. You may have a model with 38 parameters, and the range goes from, say, 0 to infinity, and then you don't have a sense yet what the best range for it will be. Then to find a good starting parameter is not an easy task. It's not actually. You're going to see it, for example, Heston. Actually, I'm showing you 4 different scenarios. I would have come up with a good starting point, but in general, it's not an easy task. How does the error surface look like? It's very important to be able to actually kind of plot the surface, like for example what I'm having here in question 3. I'm assuming this is, for example, the error surface. But you might wonder, if you have a 5-dimensional problem that we have in Heston, how would you actually plot something like this? It's a 5-dimensional kind of surface, and the minute that you go more than r squared, you can actually show it, because the height would be actually for surface, and the other two, let's just put it simply this way. For example, if I'm showing something like this, this would be one parameter, second parameter, and that would be the surface. The minute that you go more than 2 parameters, it's almost impossible to actually have any insight into the surface explicitly, but implicitly there are ways to do it. Now, one way of doing it is what I'm showing in this slide. What I'm doing is this. I'm assuming I'm starting from two absolutely, I'm picking, not starting, my apologies. I'm picking two absolutely arbitrary starting points. That means for Heston, I'm having kappa 1, theta 1, lambda 1, rho 1, and v naught 1. Let's put the 1 over here. And the same thing here, again, kappa 2, theta 2, lambda 2, rho 2, and v naught 2. Completely arbitrary, completely. And then what I'm doing is, I'm doing a linear interpolation between the two by doing what I'm doing over here. Alpha, as you see, goes from 0 to 1. When it's 0, I'm getting theta 2. When it's 1, I'm getting theta 1. That means the corners would give me the so-called theta 2 and theta 1, but in the middle is a nice linear interpolation. Then what I can do is, I can actually go ahead and for each of these theta, that means as I'm going through it, theta 0 is known, then I put it maybe theta 0.1. My apologies, I keep saying theta is alpha. For alpha 0 is clear what that one become, alpha 0.1, alpha 0.2, alpha 0.3, and keep doing it until alpha 1. You may actually make it a bit finer than this. You may actually make your step a bit smaller and keep moving along this until you get to alpha 1. And for each of these theta that you're getting, you substitute into the model. Then from the model, you get model prices. You subtract model prices for market prices and setting up your objective function, which is that root mean square error, and simply plot it. That means you're having your alpha here and root mean square error here. And then you want to see, and don't forget, when 0 and 1 corresponds to the error for theta 2 and theta 1, and you want to see in between how that surface would look like. In a way, this surface is, you turn the 5-dimensional into 1-dimensional because you're doing an interpolation, but that should give you some insight into how that surface moves as you're moving from one arbitrary set to the another arbitrary set. I'm having actually 4 different starting points for you, or 4 different scenarios. The first scenario is this. In this scenario, I'm starting theta 1 to be this data set, parameter set, theta 2 being this one. And what I did was exactly that I explained. I'm showing here my alpha, I'm showing here my root mean square error. This corresponds to the error at theta 2. This corresponds to the error at theta 1. Do not forget we discussed this. And then you'll see how the surface moves. And it seems that actually you got very lucky here. At this point, you're having a good starting point. You can extract it and start everything from there. And the error is relatively small. The error is relatively small. Now let's go to the next one. I'm again 2 completely arbitrary starting points doing exact same thing. I'm somewhere in the middle. The error is not as small as the previous case, but it still is not bad. Maybe this is a good starting point. In the third one, actually, I'm not as lucky because, as you've seen, again, 2 completely arbitrary starting points. And as I'm doing it, you will see it actually behaves very differently. It's doing a good job in this portion, but then is completely changing its mind here. That means as you were going down, which is a good starting point, actually this turned out to be a point that is kind of a maximum, not minimum. This is a local kind of minimum. This is local kind of a maximum, but it depends how service would move around these points. Now let me show you another case. This case actually is the most bizarre one, because what's happening is the one corresponds to theta 2 and theta 1. They're here, and in between, instead of is going down, is actually going up, which this is not a good way. Any points of it wouldn't be a good promising so-called starting point. What I'm doing is now I'm going to switch to the Python code, and I'm actually gonna walk you through exactly what I did here. And considering you have the Python code, you yourself could sit down and play with any other set of arbitrary points and see exactly how that surface would look like. And what it turns out, I will be, because this seems to be the most promising one, for the next few lectures, I will be using this point, which you will see, as my starting point, and as I'm going through the so-called various different optimization routines. But let's first go through the Python code, which would show you how you would come up with a good initial parameter set. One more time, sometimes this could take you a few, I'm not exaggerating here, a few hours to come up, depending on the number of parameter sets you have in your model, to come up with a good starting point. It could take you some hours by just setting this one up and simply sitting down and monitoring and seeing that how your surface would move. There are cases that you may see behavior like this, for example. Now, this is a very, very flat area, and it's very hard actually to come up with what would be a good one, because when you move into different direction, you may actually get into so-called very, very flat surfaces. Or there are cases that you may see behavior like this, and then it goes up like that, and then you're not sure actually how this would move in other directions. Then you're always trying to find a place that it moves, roughly speaking, like a nice convex if you get lucky, but for most cases you may not be as lucky as case like this that we're having here. I'm going to switch to the Python code, and I'm going to be covering the Python code. Thank you. Hello. This is the code as I promised. This is the code for the code that I actually used to generate those 4 slides in lecture 4 of model calibration. I'm going to walk you through this code, and as I said, considering you have this code, you can sit down yourself and play with various different, I highly recommend you do that. And it's a very realistic problem actually, because I'm literally grabbed the call surface from Bloomberg on Apple stock, and you see actually that just by simply tweaking and twisting some parameter set, actually could do a relatively good job finding a good starting point that you can make the model prices and the market prices match very closely. One more time, I'm importing the read plot option surface and the modules for calibration, which I'm calling it as MFC for module for calibration. In module for calibration, I'm having 2 main modules for it. One is the generic options pricing that we had, the so-called that generic FFT, which we covered during the options pricing lectures, and also the error function, the one that I call root mean square error. The parameters, let me just say shift enter here. Now the parameters are, first of all, the choice of the model is Hessen, as I said. The parameters, these are the parameters that I'm using for options pricing: alpha 1.5, eta 0.2, N12. I haven't touched this for the last, in every lectures that I'm using the modules for calibrations or even for options pricing. I always use alpha 1.5, eta 0.2, and and 12. I haven't touched that part. Now these risk-free rate, dividend, and spot, these are the parameters on that day that I grabbed the data from Bloomberg. The interest rate was 2.45%, dividend roughly around 0.5%, and the spot price Apple on that day was 190.3. Now, as I said, I'm gonna find a good starting point. I'm having 4 different cases, 4 different scenarios. I'm already, because we already went through the slides, I already know the first set is a promising starting point, as you will see. Second case is as well not as good. Third one was a trickier starting point, and the fourth one wasn't informative at all. But I'm gonna walk you through it, and we're gonna go through it, and you will see. Then let me first run this one. My apologies. Good. Shift Enter. Good. And this one also Shift Enter, which is simply what it's doing is doing nothing but plotting the surface on call options on Apple. As you see, we went through this one before you seeing it. We have the maturity here, strike here, and the surface is the call prices for Apple. Now, what I'm doing is I'm setting up exactly what we said earlier. We have 2 arbitrary starting points, theta 1 and theta 2. For alpha, which I'm calling it I, these are dummy anyway, it goes from 0 to 1, but step size would be 0.05. And as you see, each time I'm getting a new parameter set by this interpolation. Alpha multiplied by theta 1 plus 1 minus alpha multiplied by theta 2. Exactly what I described it. And the minute that I get this parameter set, I'm passing it through the so-called error value. This is the so-called root mean square error. You have the modules. What it's doing is getting that parameter set, substituted into the pricing engine, gets the model prices, has the market prices subtracted from each other, square them divided by n, and a square root of that. That's exactly what's going on here. I'm actually going to go through this E value after we are done here, just to walk you through it to see how it happens. In order to plot the surface for each of them, I'm just simply creating an array and substituting it, as you see as I'm going through it, and I'm substituting it for each parameter set. I'm finding is root mean square, and I'm putting it to an array which I call a root mean square error array. And that way I should be able to actually plot and see the surface. Let's run this one. Now this module is working and is going through the calculation, and what it does is showing to you, as it does this interpolation, is catching actually what's the smallest possible one that is going through it, and is going to actually print it on the screen. As it does that interpolation, is going through the curve and finding the smallest possible one. Let's see, it should take another 5 or 10 seconds to be out. And as I'm grabbing it, then after that, I'm going to actually plot it. Good. Now, as you see, it says for this parameter set, remember, this is through interpolation. For this parameter set, your error is this. That means on average, we are missing it by 86 cents. You may say, hold on, is that between bid and ask or not? It's not optimal yet. This is just a starting point. Now I'm going to go and plot it. Shift Enter. This is the plot. This is exactly what we had in the lecture, one of the slides. Now let me do another starting point. For example, let's uncomment this one. I'm uncommenting this one. I'm Shift Enter. I'm just going to run it now and do it again here. Shift Enter. I'm running this. Let's wait for it to come out. That was the so-called the worst case scenario. That was the non-informative one, because we didn't see that is going down. As a matter of fact, it was actually would go to a local max and would coming down. We're going to take another 10 seconds. And then I would be plotting the corresponding curve for it as alpha goes from 0 to 1. As you see, then on average is $2.84, which is not admissible. This is not a good starting point at all. And let's plot the surface for it. That's exactly the surface that I had for you. Then as you see, this is not a good starting point. The other one, scenario 1, was a good starting point. If we and then I will be using in the next few lectures, I will be using actually that promising starting point as the starting point to find hopefully the optimal parameter set. Thank you. Welcome to Model Calibration Lecture 5. In the previous lecture, we discussed how at least one way of coming up with a good starting point. And if you remember, I said I will be using that starting point to get hopefully to the optimal parameter set. Now, that starting point, then what we are doing is now we have a promising starting point, and the next step for us is having the starting point, having our cost function, and knowing that what part of the data we'll be using, be trying to find the optimal parameter set. And for that one, we need to do some kind of a optimization. Now, when it comes to optimization, there are three major ones. The brute force or grid search approach, gradient-free routines, or one example of it is the Nedler-Mead simplex algorithm, which is gradient-free routine, as I said, and the gradient-based routines. One example of it is BFGS algorithm. I showing this one in red because in this lecture my focus would be completely on brute force or grid search approach. Now, for this one, what we are doing is we are actually performing an exhaustive search in n-dimensional space for all possible candidates. You can imagine by just saying this is kind of tiring. It's a very, very expensive routine. Actually have pros and cons of these routines. The pro with this routine is it actually guarantees global minimum independent of the shape of the objective function. By independent of the shape, I mean when it comes to the objective functions may not be as smooth. You may not see something like this. It might be something which is kind of jaggedy, or it might be something that has tons of local minimum and local maximum. Then what happens is no matter what kind of a shape you're going to have for objective function, if cost is no problem to you and you can really cover all possible candidates, this routine guarantees that you can find global minimum. Having said this, you can imagine when it comes to the cost, computational cost, you can't just ignore it. Then what it happens is, as I said it earlier, is pretty expensive, not feasible for higher dimensional problem. For example, let's go to Heston. When it comes to Heston, which is a 5-parameter model, let's say on each grid you have, my apologies, for each parameter, let's assume we have 10 possible, we set up a grid with 10 possible values. For example, when it comes to kappa, for example, you may set up kappa from 1 to 10. When it comes to theta, you may set it up from 0.1 to 1. Let's assume we believe that is not less than 0.1, we believe is not more than 1. When it comes to lambda, we may assume it's from 0.1 to 1. When it comes to rho, we know it's between -1 to 1, and we set up, moving by 0.2 would be 10 or something close to it. And when it comes to V naught, again, we may do something from 0.1 to 1. Now, for this case, it would be 10 to the power 5, which is about 100, not about exactly, 100,000. Then you need to do 100,000 RMSE, root mean square error. Maybe 100,000 is not that bad, but remember, this is pretty coarse the way you're doing it, and it doesn't mean it's a global minimum. Having said this, let's say we are agreeing with this, but what happens if you go to a model which has 13 parameters? Then you could imagine 10 to the power 13 becomes pretty expensive. And for a model like that, still there is no guarantee, because you need to cover, as I said, all possible candidates. All possible candidates does not mean that maybe kappa would end up with 10, why not 20? There are cases that actually kappa would be more. Then, as you see, it's very expensive, not feasible for higher dimensional problems. And this is the so-called becomes curse of dimensionality for us, that I'm kind of maybe repeating myself here. As a problem number of parameters in the model gets larger, then you run into this huge computational cost. Having said this, if computation would not be an issue, everybody will be using brute force search. The other thing about it is, as you will see it in the example we're going to have, as these numbers start growing, I mean, things could take, actually, if not days, would take hours for it to converge or to find the admissible solution. Now, what we are doing is we're doing grid search around a good, promising starting point. Then I call it around a promising starting point. We got that promising starting point from the previous lecture. That was what we got from the previous lecture. If you remember, when we tried various different scenarios, and we saw that in one of the scenarios, we got this root mean square error for this parameter set, and I call this one to be my initial parameter set, and I build a grid search around it. By grid search around it simply means if I'm having 2.3, then maybe I do 1.8 to 2.8. When I'm seeing this one, maybe I do 0.036 to 0.056. You see around it in a symmetric way, and you could see the rest as we're going through this. Now, this is how I'm setting this one up. The brute force algorithm is nothing but a nested for loop. Then what I'm doing is, for the kappa, for the theta, as you've seen, these are exactly what I discussed as far as a search around the starting point. For the lambda, for the rho, for the V naught. What I'm doing is I'm calculating E, which E means that root mean square error. First, I'm starting from some very, very large error. And any of these, as I'm going through this next would be less than what I'm starting with. I'm setting this to be the so-called the new E, and the optimal parameter to be that theta at that point. And I keep doing this, and at the end, the optimal parameter set is the one with the smallest E. That's how actually this process works. One more time, you see it here that you have to have a good, promising starting point to do your search around it. Otherwise, this loop, instead of being from 1.8 to 2.8, you may have to start it from 1 to something like 10 or 15 or 20, whatever that might be. And the same thing for theta, lambda, rho, and V naught. It turns out if you do this, the optimal parameter set that I'm getting is this one, and you look at the error. The error from 86 cents goes down to 36 cents, which is relatively pretty tight. Is actually, for our grid search, this what I call actually optimal parameter set and optimal root mean square error, which would be the one that I have. I'm plotting actually the model versus the market. The model, I'm showing it with the X. The model, I'm showing it with plus. And as you see, I'm showing it, I'm explaining each color corresponds to which maturity. I'm going from the short maturity to the longer maturity. And as you see, they're actually hard to distinguish here. They nicely, closely actually match. Very nice. I mean, in some cases, you see there is a difference between them, of course, here as well. But overall, they're actually doing a very nice. The reason I'm plotting it that way, because I wanted you to see it for each maturity separately. Otherwise, if I would have done the surface against each other, it would have been very difficult to actually distinguish between the two. It's actually doing a very, very nice, very decent job for this case. Now, what I will do is I will go through the Python code for you to see how I've done the setup, and we're going to actually run it together and make sure that we see exact same results. Hi, this code is, I'm going to go through this code providing exactly the results of what we had on grid search. As usual, we just importing the modules for calibration, which we need, and some of the libraries that we need for what we are doing. Exactly as before, for parameter set of the parameters that we need for pricing, the model pricing, we still use exactly what we used in the past. Alpha 1.5, eta 0.2, and 12. Model is Heston, no change there. Risk-free rate on the day that we actually extracted the options prices on Apple stocks. Interest rate was 2.45%, dividend roughly 0.5%, and the spot price, the stock for Apple on that day was $190.30. Let me do Shift Enter here. We are plotting one more time the surface. We just want to make sure that we seeing the surface for the Apple. These are the market prices. Now, what we are going to do is we are going to do a grid search around the starting point. That was the starting point that we found in our previous lecture. So it's very important we have a good starting point. And that was for kappa 2.3, theta 0.046, lambda 8.25%, correlation minus 53%, and V naught is 0.054. Then what we are doing is we doing a grid search. That's exactly the code that I had in the slides around this starting point. Is a nested for loop for kappa, theta, I call it sigma, and lambda is the same thing anyway. Rho and V naught. This is going to be 243 iterations. In order to save time, knowing that I know roughly, not roughly, exactly what the optimal parameter set is, I'm going to narrow it down. Instead of going from 1.8 to 2.8, I'm going 1.8 to 2.3, because I already know that it would be in 1.8. For this one, I'm doing 4.6 because I already know it. I'm going to save time. For that one, I'm starting 825 to 925. On that one, I'm using actually -63 to 53 just to save time. You can go back and do it yourself. And for the last one, I will be using actually 54. That way, it would be much faster for us. Then as I'm going through this one, anytime I'm seeing the root mean square error going down, I call this one as the new so-called optimal parameter set through my grid search. Let's run this. Shift Enter. And as it's going, you can actually see the results here. It gets printed on the screen. This should take just maybe a minute or two. And then as you see, it's going through it. You're seeing the results. New 68 cents so far, 37 cents. That's much smaller. And I think that's actually turns out to be the optimal one that we had. No, 36 cents actually. 36.7 cents. and it should be just 32 iterations. That should be quick. I think we are almost done. You can imagine one more time, as I said, the cons about this model is very expensive. It takes, for this case, which is not so expensive, still you need to be patient as you're running this. Sometimes you may need to run it overnight and see the results in the morning, and actually sometimes longer. Then as you see, it's telling you the solution of grid search is this. That's the solution for this optimal. That's exactly what we had in the slides in the lecture. Now let's do the plotting, model versus market. That was, yes, that's exactly what I had on the slides for you as well. One more time, as you see, the X are the market, the plus are model prices, and the colors are different maturities, and actually you're doing a very good job. Few discrepancies, which is fine, but overall discrepancy of 36 cents, not too bad. But one more time, even though it's a very, very realistic example, because we just grabbed something from Bloomberg and Apple, we put it in, we did the grid search, we got lucky in finding good starting point. You can imagine it's not always easy to come up with a promising starting point, and also the very optimal one, your grid search needs to be narrower, and that would take actually longer time to do it. But you have the code, you can play with the code, and actually I'm gonna grab a few different cases for various different option prices, maybe on different stocks, and I'm gonna ask you actually to replicate these results using grid search for those examples as well, which will be part of your assignment. Thank you. Hello, welcome to Model Calibration Lecture 6. In Lecture 5, we discussed the various different optimization routines, and the first one actually we covered was the brute force, and I mentioned that if computationally there wouldn't be any issue, definitely that would give us the global minimum, but knowing that actually that's not the case, then one wonders, are there routines or not? And we said in general there are two other methods. One is gradient-free method, which the most famous one is the Neldler-Mead simplex algorithm, and the one after that would be gradient-based. On this lecture, we will discuss the simplex Neldler-Mead simplex algorithm. That would be the so-called gradient-free routines, and the most known one is the, as I said, Neldler-Mead simplex algorithm. Now, what this algorithm is about, it actually performs a search in n-dimensional space using heuristic techniques. You may wonder what I mean by that. I'm not actually going to delve into it. The only thing I would tell you is actually in optimization package in Python, the Skippy optimized, the fmin is actually providing that algorithm, which in the Python code that I'm providing to you, I'm actually explaining to you how to use it, how to specify its parameters, how to run it, and I will be exactly following exact same example that I did for brute force. I will doing it for this one as well. Just emphasizing one more time that this algorithm uses just function valuations. There wouldn't be any need for first or second derivatives. Now, before we go through it, just discuss some pros and cons. By no means that would be the entire list, but these are the so-called the most known ones. The pros, of course, no derivatives is required. The objective function does not have to be a smooth. This is very, very important. That means we don't have to worry about the shape of the objective function. In case that we will be using gradient base, you will see it would be of concern to us, But for this case, we don't have to worry about the shape of the objective function. Then in that regard, as I said, does not have to be smooth. Now, cons immediately. I mean, there's some pros, but let's see what would be the disadvantage of using this method. It becomes actually pretty efficient in high dimensions. And the other problem with it is actually it could take lots of iteration with almost no improvement, even though you're far from the so-called minimum. That's another known fact. And as usual, for most optimization routines, there is we cannot guarantee that actually the solution that we're getting actually is a global minimum. As I said in the previous case, I'm using for all this optimization routine examples, I'm using from the same starting point. That was the starting point that we use for brute force. This is also the starting point that I'm using for Nedler-Mead, and that would be also the same starting point that you will see in lecture 7. I will be using it for gradient-based routine. If you remember, for this starting point, the root mean square error was 86 cents. That means on average, the difference between model price and market price is about 86 cents. That's just a starting point. Now, if we run the routine, which I would go through it, what we would get is actually we go from 86 cents to almost 28 cents, 27.9. Not bad. And the so-called optimal parameter set for it would be this parameter set. This is, one more time, that's for kappa, that's for theta, that's for lambda or sigma, some people call it, the wall of Wahl. This is called the so-called wall of Wahl. And the correlation and the starting variance, which is V naught. I'm going to show you market versus model through the fit. What's important here, I explained this, as you see, we definitely doing a good job, but on the short side, as you see, we see relatively bigger discrepancies between model and market. When it goes to longer one, actually we see it's much, much tighter. Here it's almost impossible to distinguish between model and market. By shorter one, actually we see a bigger discrepancy. That's a known fact for Heston model, because shorter maturity skew is higher, and that's something that actually Heston doesn't capture as well. Now, as I said, you're having this code. I definitely expect you to start playing with it. And of course, I will be providing in some of the assignments a snapshot of some of other option surfaces. This one was on Apple. I may give you something like, say, on S&P 500 index, and then you will exactly following the same thing, and we'll see if you can do a good job, a good fit, the way we are doing it for this one as well or not. Now, I'm actually doing two more things here and two more slides. What I'm trying to show you is you may go back and look at this solution from Nedler-Mead, and you wonder how far that would be from what we got from brute force. That's what I'm doing here. I'm actually showing the error surface between the so-called optimal parameter set that we got from brute force in lecture 5, which I'm providing it here, and the optimal parameter set we just obtained from running Nedler-Mead. And what I'm doing is I'm actually doing exactly as we did it when we wanted to find out the starting point. I'm doing an interpolation between the brute force parameter set to Nedler-Mead parameter set. But this time, actually, I'm kind of extending it. As opposed to having alpha just being between 0 and 1, nobody would stop us trying it between, say, minus 0.5 to 1.5. I intentionally do this just to see how the surface looks like. The result that I'm getting, I'm actually presenting it over here. If you pay attention, this is in red is the one corresponds to Nedler-Mead, and the one over here corresponds to brute force. And because I'm having from minus 0.5, which is here, alpha, to 1.5. As you're seeing, I'm kind of going out, and you'll see that actually nicely, it turns out that I'm seeing a very nice convex behavior, which nicely Nedler-Midge actually caught it. Now, one more time, on this axis, I'm having root mean square error, and this is simply one way of showing a surface which is a 5-dimensional, but instead of this, I'm just showing the root mean square error, because showing the surface is impossible, but showing the error, which is 1-dimensional case, is easy, as exactly I'm presenting it here. Then what I'm going to do is I'm going to switch to the Python code, explaining how to set up the fmin function from Python, and how to run it, how to set up its parameter sets, and actually get the optimal parameter coming out of the Nedler-Midge. Thank you. Hello, this is the continuation to lecture 6. We discussed model calibration for the case that we use a gradient-free optimization routine, and as I said, the most common one is Nedler-Midge. I'm going to actually go through the code, explain to you how to call the simplex algorithm, Nedler-Midge simplex algorithm, and actually the results that I showed you on the last few slides of lecture 6 is actually coming exactly from this code. Now, one more time, the few things. One is I'm importing read plot option surface. You've seen this before. It's simply plotting the surface for the snapshot that I had on Apple stock, the option on Apple stock. The modules for calibration, I'm importing it, and in short, I'm calling it MFC. And as I said, the Python action is an optimization package, has the Nedler-Midge algorithm. Is called fmin, which I'm actually importing it from Skippy Optimize in Python. The rest of it, you've seen it before. Let's just say Shift Enter. Now, the parameters exactly as before. I haven't touched this at all. For the pricing module, the options pricing module, alpha 1.5, eta 0.2, and 12. I have not been playing with this at all at this point. The model, as before, Histon, stochastic vol, risk-free rate, dividend, and spot price. On that day, as you remember, for interest rate, we had 2.5%, dividend rate almost 0.5%, and the spot price for Apple on that day was $190.30. Now let's say Shift Enter here as well. I'm plotting the surface. The surface got plotted. That's the surface on Apple. One more time again, as you see, I'm having, I'm sorry, I can actually touch this surface. You seeing these are for longer maturity. These are for shorter maturity for call options. And at this point, I'm just focusing on call surface. Now, for the Nedler-Midge simplex algorithm, fmin, the starting point as before, as I did for all, are given here for kappa, theta, lambda, rho, and v naught. Now, that's the parameters that I'm starting. The routine, as I said, is called fmin. But before doing the routine, a couple of things I have to emphasize. In order to see the progress report in Python for optimization routines, what you need to do is you need to set up something which is called callback function. You can call this a dummy name, actually. You can call it whatever you like. I call it callback f or callback function. If you want to see the progress report, if you don't have this, you have to wait until the very, very end, and then you can see the results. But sometimes people want to see the progress report. For that reason, you need to set it up. And the way it's getting set up is as simple as just simply what I'm setting up here, which is pretty generic. Inside this xi is the so-called parameter set, is again a dummy name. You can call it whatever you like. It gets passed into this so-called error function valuation, which I call it e-value. This is inside the module for calibration. You have the code, you can see it. That's exactly the name of the module. I'm passing this xn, and the arguments are what gets passed through pricing routine that you've seen it before. The market prices, maturities, strike, dividend, interest rate, dividend, spot, alpha, eta, n, and model. This is something that I'm not, is already you having it, you're simply passing it through. And when it comes to the routine, in the routine, the very first argument is the so-called error function, you passing the error function to it, which in our case is mfc.e-value. The second argument is the parameter set that you're passing, which is the parameter set, which is the this parameter set, the starting one that we have. And any argument that it goes inside that error function should go through args equal to this set of argument, which I'm calling it arg. This arg is not dummy name. It has to be args for all the arguments. But the other arg is actually dummy. You can call it whatever you want. That means if you change this arg, you have to change this, you have to change this, and you have to change that one as well. But that's a dummy name. You can call it whatever you want. You have to set up the tolerance on x, which means on the parameter set, but tolerance means if from one parameter set to the next in the iteration, some kind of a norm would be below 1/10,000 or 10 to the power minus 4, it's gonna stop. Function valuation. If the value of error function, the way it goes down is it becomes less than this number, you're gonna stop. Max iteration, you may set it up to whatever you want, but at some point you have to have some finite number for it. Typically, I have something like 200 or 400. I'm setting it to 20 for you, just for us to run it and not waiting here for 10, 15 minutes. But in the slides, the result I provided you, actually I had it at 100. You can set it at 100 and just seeing that the kind of results you may get. It does not mean that it would converge. It simply means it would stop the minute it gets to that max iter. If you want something to converge, you need to set it up to a much higher number. I'm setting up to be at 20 here. Max function is the maximum function evaluation. I'm setting up to be at 100. Callback is equal to this callback f. This callback, you have to call it, but if you call this none, that means, or 0 or something like that, that means you don't want to see the progress report, but we already have it. We set it up and we want to see the progress report. The rest of these things has to do with, at the very, very end, how much statistics you want to see. When it comes to display, you want to see it. When it comes to retail, you want to see the entire thing or not. And the full output, you want to see the entire output or not. I mean, that's something that you can definitely Google it. You can simply get familiar with it. But what I'm having here, that should simply work by simply changing some of these names. Let's run this. And I'm running it. Sorry. It should be a start actually running here. In few seconds, you will see as the results coming out, is showing your iteration, is showing the parameter set, and is showing the corresponding value for the error function. Yes, it's from 68 cents, it went down to 66. 54 cents now. Didn't go down. Hasn't gone down yet. Went to 35 cents. Not a bad job. So far, so good. Just after 5 iterations, 34. Still at 34.9. Still at that number. Let's see. 34.9. 32 cents now, went down by 2 pennies. Still at that number. Remember, it's just 20 iterations we are doing. 30 cents, not bad. 29 cents. 3 more iterations and you're gonna stop. Yes, it stopped. The best one that it got after 20 iterations, it says warning, maximum number of iteration has been exceeded. That means by no means is optimal, and we know it. What I had in the last slide of the lecture was the one that I had it after, I believe, if I'm not mistaken, after 100 or 150 iterations. I don't recall it exactly, but anyway, you can run it yourself and see it for yourself. The optimal parameter says for this iteration is this with this corresponding value. Now let's go ahead and just plot it against each other. That means getting that parameter set, substituting it into the engine, creating a surface for model prices, looking at it versus the market prices. This is market versus model, exactly what I had in the lecture as well, coming exactly from here. One more time emphasizing that, I think I've been saying this a few times, that on the short-term maturity, actually we're saying that we are missing a bit. On a longer maturities, we're doing a good job. If you look at the difference between the so-called the market versus the model. But overall, we've done a decent job. Thank you. Hello, welcome to Model Calibration Lecture 7. In Lecture 5 and 6, we discuss optimization routines, and we said in general there are 3 major ones. We discussed brute force search. We discussed the gradient free routines. The main one was actually the Neller-Mead. And now today in this lecture we'll be discussing the gradient-based routines. There are tons of them. For this example, for this lecture, I'm actually discussing BFGS algorithm and Broyden, Fletcher, Goldfarb, Shano algorithm. This algorithm is actually, as I said, I'm not going to delve into it for one reason for it is because we in Python Skippy optimize the package, optimization package, actually provides the BFGS algorithm. It's just what I will be doing is I will be discussing, as I did it previously, the pros and cons, and also I'm providing you an example, a working example, or a continuation of the example that we had already, and just showing you how to set up the parameters of the algorithm, how to call it, and what to expect to get. Now, just a little brief thing on it. It belongs to the so-called quasi-Newton methods. Is an iterative method for minimizing an objective function like all other optimization routines. And as I said, in Python, actually Python provides it, and what is called is called fmin_BFGS. Now, the pros and cons, in short, by no means is not all advantages and disadvantages. Those are the most common ones. The most known one when it comes to, I would say, advantage of this method is it converges really fast for the case that objective function is convex or close to convex. The known disadvantages, one is it gets stuck on a saddle point. That means if you have a surface which is relatively flat, and then if you're somewhere around here, you may get actually stuck and doesn't know where he's going because it's a gradient base, and around that area, gradient is 0. And that's actually a very known fact. This is one of the difficulties in any kind of, anytime you're trying to minimize an objective function, is a known fact in deep learning specifically because the objective function has lots of parameters and you run into a lot of these flat surfaces. Now, the other thing about it is the objective function should be relatively smooth for these things, because if it's jaggedy or you see a lot of, and when I'm saying smooth, is doesn't mean, I mean smooth in the sense that not having too many of these flat surfaces either. Now, as usual, as we said it in the past, there is never a guarantee that the solution is the global minimum. Remember this. You may be, in a sense, you may have a very, very flat surface, some local minimum, again a flat surface, maybe some global one, but for some reason you may come over here and never seeing actually this point. Then there is never a guarantee that you get into the so-called global minimum. Now, then what people do is, in general, is that they really try various different starting points to see where you would end up. This is not what I will be doing here, but it's definitely something that I will be setting up for a homework assignment. And what you will be doing is, for the same problem that I have, I give you various different starting points to see if you would end up roughly at the same place or not. Now, as usual, as I did it in the past lectures, the starting point is always the same. I'm using exact same starting point. That's the starting point that I did it for brute force. That's the starting point that I did it for simplex algorithm. That's also the starting point that I'm using for BFGS algorithm. Now, for this starting point, if you remember, the root mean square error was 0.86, which is about roughly 86 cents. Now, when you run the algorithm, which I will be actually going through the Python code, what you would get is, for the solutions, you would get the following parameter set. One more time, that's for kappa, theta, lambda or sigma, rho, and V naught, the parameters of the Heston stochastic volatility model. And the optimal root mean square is 26 cents. That's the best we've ever done so far. One more time, I'm not saying that that's truly the best you can do. It's just a matter of seeing that if you come up with a different starting point, you can do a better job or not. In the lecture 5, I believe, lecture 4, lecture 5, I think it was lecture 4, I said a good starting point is extremely important because you may actually get the better results at the end, but hopefully what we've done here is actually not that bad. This still is a very, very good fit. 26 on average is not a bad job on roughly about 160 options, because I'm just looking at the call side. I had overall 300 something. I looked at half of them just on the call side, roughly about 150, 160. Now, as usual, I'm plotting after I'm having this optimal parameter set. I can create a surface for the model, the model prices. I'm going to go through the code. You have the code, you can play with it, see exactly what I'm talking about. Then you have the market, you have the model, and I'm plotting, as I did it in the past, model versus market for every maturity. Again, I'm plotting it here. Again, the observation is that on the shorter maturity, typically you see we miss more on the shorter maturity. When we go to longer maturity, we're doing a very good job. You may see some discrepancy here, but definitely you see overall the shorter maturity is what we miss more than longer maturities. Here or over here is almost sometimes impossible to distinguish between the two. Now, as I did it in the previous lecture, here I'm actually gonna go through saying that now we have the optimal parameter set using BFGS algorithm, which is gradient based. We also having two other parameter sets, one coming from brute force, one coming from Nelder-Mead. Then what I've done here is I'm actually trying to bring the error surface. When I'm saying error surface, because I'm just looking at the value of the error function, which is that root mean square error, what I'm doing is I'm actually doing that interpolation between these two parameter sets, namely brute force versus the BFGS, and I'm just doing interpolation, and any theta that I'm getting, I'm actually plugging it back in, getting all the market prices, model prices, calculating the error function and actually plotting it and saying that how that, as I'm moving from one parameter to the other, how the error function looks like. Then on this slide, I'm looking at the error surface between the brute force and BFGS. That was the optimal parameter set coming from brute force. This is what we had on lecture 5. This is optimal parameter set coming from this lecture. And that's the interpolation. As before, what I'm doing is this time I'm using alpha from minus 0.5 to 1.5 as opposed to 0 to 1, just having some going out and having a better picture of the surface. And actually the surface looks kind of a bit funny here. When I'm looking at the surface, this is the BFGS, the corresponding error function for that. This part, which I'm showing it in red, is for the brute force. That's the brute force. This is the BFGS. And if you see in between is pretty smooth, but when you're going out, actually this one is not too bad, but look at how jaggedy this one gets. That's actually a very nice case, and one can actually play with some of those parameters as a starting point and see what happens. There are literally infinitely many ways to do these things because there are infinitely many different starting points, and see where you would have end up. In the next 2 slides, what I will do doing is actually now this time I'm saying that I have the optimal parameter set from Nedler-Mead. I have it from BFGS. Now why don't I go ahead this time and actually do error surface between these 2 parameter sets? The one comes from gradient free and the one comes from gradient based. And remember, this is what I had in the previous lecture, the parameter set from the previous lecture. This is what I just got from this lecture. And exactly, again, I'm having alpha between minus 0.5 and 1.5, and I'm plotting the surface. One more time, these points corresponds to BFGS. This comes from Nedler-Mead, and the extrapolation, this part is the extrapolation part, this extrapolation part. Again, in between, as you see, it does some kind of a funny behavior as opposed to being convex. Actually is, how should I say, is the not convex up, convex down. And you'll see if you would have started maybe this point would have been a different scenario, or actually over here you might have gone to either way. I mean, these are things that you can test it yourself. Now, one more time is very, let's mention 2 things. One is a starting point is extremely important. A good starting point would take you much closer to so-called optimal parameters. So the bad starting point, depending on the routine, you make a complete loss. The other thing is, if computation is not an issue, and then you can simply do an exhaustive search, then the brute force definitely would take you to the global minimum. I mean, this is theoretically. Knowing that computational is impossible to go through every parameter set, knowing that, then the most important thing is knowing that you should start from a good starting point. You can build something around it, as I did it in the lecture 5, and then that way you would have a good understanding of how your surface looks like, and then you can use that starting point inside either a gradient free or gradient based. In general, depending on your understanding of the cost function, you decide which objective function to use. If you believe your objective, which optimization routine, my apologies. If the objective function is, you believe is relatively smooth enough, then definitely something like BFGS would do a great job. If you think it's pretty jaggedy, then you would be better off to use something like gradient free, something like Nedler-Mead. Thank you. Hi, even though I felt maybe it would be good to just go through another Python code for that loss function surface that I was playing with at the end of lectures 6 and 7. Even though the code is completely similar to the code that we use for different starting points, but I thought it would be good to just walk you through the code one more time. I'm providing the code to make sure that you know where it's coming from. Then here is the code. You're very familiar with this one. You've seen it a few times. Again, I'm importing modules for calibration, and I call it MFC just in short. And also read plot option surface. It's very important to always look at that option surface and exactly knowing what we dealing with and what kind of, how does it look like. As far as how does it look like, I mean, if it's smooth enough or not. Anyway, let's do shift enter here. Exact same parameter. That part I have not touched at all. The same risk-free rate, dividend rate, and spot price. Now, as you're seeing, I'm having three different, oh, I said three, but it looks like as if it's two. Let me correct this. Good. Now, the set one is the brute force versus Nedler meet. That means I'm having the optimal parameter for brute force, optimal parameter for Nedler meet, and I'm going to do interpolation between the two, just see how the surface looks like. The second set is now brute force versus BFGS. And the third set is Nedler meet versus BFGS. Let's say I want to just run, because that was the most weird looking one. I'm going to actually do just the second set, and you can play the other two yourself. Now, then I'm setting that's the first one was the optimal parameter set that I got from brute force. The second one is the optimal parameter set I got from running BFGS algorithm. That's done. I'm plotting the surface again. Good. And what I'm doing is I'm doing interpolation on from minus 0.5, as you see here, to 1.5. And as I'm doing this, each time I'm finding the parameter set, I'm sending it inside the error function, and what I do is I'm simply, as I'm going through it, I'm appending it to a vector and plotting it against each other. Let me do this, and as you see, as it's going through it from minus 0.5 to 1.5 is actually showing each of these parameter sets, each going in for valuation of these root mean square error. And as I said, I'm appending into a vector and plotting alpha versus root mean square error. That's the run is just going to take roughly about a minute. And then at the end, I'm plotting it against each other, as I said. You can make the step size a bit maybe wider or make it a bit coarser just to save some time. But at this point, I'm setting it up to be at 0.05. It just needs to get to 1.5, maybe another 40 seconds, 30 seconds. You have to pay attention when you're doing that interpolation, extrapolation, whatever you want to call it, from minus 0.5 to 1.5, you have to make sure that the parameters are admissible. You cannot have, for example, kappa being negative. You can have theta being negative. I mean, these are things that I will be emphasizing later, but I'm already aware of the fact that when I'm doing minus 0.5 to 1.5, every parameter set that I'm saying in these sets of parameters is all admissible. Am I done almost? Let me see. The answer is just one more. It didn't come. Let's see, maybe that was the last one. This is the optimal parameter set, and let's run it. That's exactly that weird looking surface that we are having. If you remember, This corresponds, one more time, as you're seeing in red, that corresponds to the one for BFGS, that corresponds to brute force, and that was exactly the shape we had. One can imagine if you start from here, you may get actually stuck here, never coming over here. These are things that you can try it for yourself to see. You can go ahead and, as I said, switch to the other one, and you have this code. This code is exactly the same as the code that we use for finding a promising starting point, but this time, because we had a couple of parameter sets from various different optimization routines, I just wanted to do this interpolation, extrapolation for you to see how does the error function surface looks like, and actually it's showing that in some cases it actually could be some weird looking surface. It's not always a nice convex surface. Thank you. Hello, welcome to Module 1 coding parts. I'm going to go through the code. It's a very, very simple code, as I mentioned it through the lecture, just for you to have it and to be able to play with it. Here, let's just load the packages. And for zero coupon bond, assuming that I'm assuming constant rates, two different rates. I'm assuming low rate of 4% and another rate of 10%, which is relatively higher than the other one, no question about that. And as you see here, we simply assuming, I'm assuming this rate is instantaneous compounded short rate, and the zero coupon bond for it would be nothing but exponential of minus RT, which I'm having, as I said, two different ones, R1 and R2, and just a simple plugging and plotting. This is exactly what we had in the slides in the first lecture. The only thing is I just want to show it to you that if you change, for example, if you make this go to 1% and the other one going to 20%, for example, you'll see that the first one would become almost a straight line and the other one become pretty deep. That's exactly what we are having over here, just for you to see. And let me see this part. I should maybe change the size for you to be able to see it. But anyway, I'm sure you know what I mean by that. Let me see that. And this is, yes, good. This is, sorry. This is exactly what we are having over here. Good. That's just was the code that we had for the first lecture. One thing that you can try, actually, I may assign this one actually as a homework, is you may assume for 30 years, we're assuming the rate is constant. We may assume actually maybe 4 different rates for the first 5 years, then 5 to 10, 10 to 20, and 20 to 30. And then you see that the shape actually would be different. You start from a very low rate, then you go to higher rate, then it would look kind of a, first start going convey and then becomes kind of convex. Thank you. Continuing on lecture 2 on interest rate instruments. This lecture I'm focusing on swaps now. The definition, this is a very generic definition. A swap is a simultaneous selling and purchasing of cash flows involving various different currencies, interest rate, and a number of other financial assets. The one that I will be focusing on actually would be simple interest rate swaps. They're actually pretty liquid. A simple interest rate swap can be actually, we can easily decompose it into its constituents. And as actually by doing this one, you would actually will see how forwards and options would play a role into swaps. And as I said, my focus would be on simple interest rate swap. It's the way I would be starting is this. In its simplest form, as I'm saying here, an interest rate swap would be between two counterparties, A and B. And the way it works is that we're assuming that, for example, counterparty A needs a $1 million floating rate loan. Just think about you want to get a loan or you want to get a mortgage but then you don't want a fixed rate, you want to actually get some floating rate because you believe that at some point maybe mortgage rate is high now, but it could go down depending on the interest rate. And as opposed to fixing it, you want to go with a floating loan. But on the other hand, counterparty B wants to get or needs a 1 million fixed rate loan. It's important to recognize that, for example, international companies, when they exporting their goods, they need to get to some of these instruments in order to protect against the raise in the currency. Like, for example, if there is a German company who wants to sell their cars to US, and let's say the euro goes up, then the price of the car would go up for US, and they may actually lose the US customers. For that reason, what they do is they get into some of these contracts to protect against rising prices for their export cars. Now, an example like this. Now, it turns out, for example, in some cases, or because of market condition, or because of the relationship with various different banks, for example, counterparty B has could get a better rate in borrowing at floating rate, even though counterparty B needs to take a loan on a fixed rate. But for some reason, counterparty B has a better advantage for floating rate. On the other hand, maybe counterparty B has an advantage on the other side. Then what they do is they would decide to actually use this comparative advantage, and each could borrow on what they have a better advantage. And what they do is they do swap against each other. That means A would borrow 1 million at fixed rate, even though it wants the floating rate, and the interest that they receive from B, they pay it back to the lending bank, and then the B would borrow 1 million at the floating rate, and the interest rate payment received from A, they would pay it back to their lending bank. In a way, they do a swap that way. Now, knowing that in the beginning, the initial sums are the same because they both got involved into something which has exact same so-called notional principles, then what they're doing is they do not have to exchange anything. They're not exchanging anything. They're just getting into a swap, agreeing that one would pay fixed, the other one would pay floating, and they're just simply getting into the swap. The interest rate payments, they are typically on the same currency, and then the only thing the counterparties would do is they exchange the interest differentials. That means if one receives more, depending on what the rates are, would pay to the other one. If on the other hand, if the other one supposed to pay more than the other counterparty, then the second counterparty would receive the differential. At the end, both counterparties will secure lower rates. Remember, they take advantage of it that way. And what's happening is the dealer who takes care of this by going through what they committed, because it has to go through a dealer or broker, they just earn a little fee on it. We can think of swap rates in terms of forward rates, because it's easy to see that the swap can be viewed as a portfolio of forward rate agreements. That's exactly, if you go back to the definition of forward rate agreement, you will see when you think about this floating rate, that floating rate would be exactly set up exactly like forward rate agreements. Now, each cash flow is a cash flow of an forward agreement with a fixed rate equal to the swap rate S. The way we will be finding it is we're looking at all the cash flows coming for the fix, all the cash flows coming from the floating, which I'm going to go through it in an example. And as of today, we're making those two the same and or making them equal, and that what would exactly give you the swap rate S. And the reason for it is because if one today can take advantage of the rate, there would be an arbitrage. That means the market, today's market, no arbitrage condition would actually set up exactly what that swap rate is by looking at what the floating rate is as of today. Let's look at the terms to make sure that we can clarify this a bit. First, let's look at the terms. The most popular terms for swap rates are 2, 5, 10, and 30. Of course, we have 3, 7, and 15 as well. But then these are the most popular ones, 2, 5, 10, and 30. On the payments, as I said, we have fixed rate payment and we have floating rate payments. In US, there are 2 semi-annual payments according to the fixed rate. That means day one, the rate is already fixed. The payment on the floating legs, there are typically 4 quarterly payments. That means the way it works is this. As we're getting in today, let's say this is today, and let's say I'm assuming a 2-year swap for now. That means I'm dividing this one up for 6 months, but considering that I have quarterly here, then I'm dividing this one now to 8. Then this is 1, 2, as I said, is a 2-year swap. Then on the fixed side is every 6 months. This is the fixed side. This is the way I'm receiving the payments. On the fixed side, they're all exactly the same as you see because it's fixed day one. On the floating side, every 3 months, and depending on the floating rate, that's why I'm showing it as these curvy lines. It might be go up and down depending on what the rates are. This is the way it works. Then we have 4 fixed rates every 6 months, starting 6 months from the inception, and then 8 floating ones, the first one 3 months from inception, with, of course, you have to pay attention to the settlements because there is maybe 2 business days after. I'm not getting into any of those at this point. One more time, again, there are 4 quarterly payments per year, and LIBOR, 3 months LIBOR is actually becomes a floating rate. I'm gonna explain how that works, and it gets reset quarterly. That's why you see these changes. That means as we're going through time, depending on what the 3-month LIBOR is, it gets reset for the next payment. Hello, I'm going through the codes for module 3. In module 3, we did a lot of plotting for the data I provided. We provided, as I said, I provided swap and LIBOR rates for 4.5 years. We just do exactly the processing that we did in lecture 3. Just gonna go through the code. First, we're loading the packages as usual. Here, I'm reading and pre-processing the data provided to you, putting it simply in the data frame. That part should be pretty easy. And as you're seeing here, starts from January 2nd, 2014, going to October 11th, 2018. The first 1, 2, 3, 4, 5 are the LIBOR rates. From 1 month to 12 months, as I mentioned earlier, and for swap, starting from here, which will go from 2 to 30. First, we plot the curves for LIBOR, and we pick, as you remember, as you recall, we actually plotted 5 different curves on 5 different days. And here are, as you're seeing, I'm doing the very first one. 300, 600, 900, and the very, very last one. You can pick any date that you want. That shouldn't be that difficult, and that's exactly the curve that we had in the slides. The blue one is the very, very first one, and the purple one is the very last part of the data. And as you're seeing, it consistently been going up, but it's kind of a parallel shift. And this has to do with the fact that Federal Reserve been raising rates. Of course, from 14 to March 15th, the curve was almost no change because Federal Reserve didn't take any action, and the action started actually. You'll see that from 2016 May 17 and 18. It's been a few raises in 2018. We go through now. We go through the time series of them. This is the exactly again the curve that you've seen. We had it already, and let me see. We may need to make this one a bit smaller to be able to see it, but you can change the size if you wish. Here I'm having 18. Maybe I change this one to say 12. Just to be able to visualize better. That's it. That's exactly the slide that we had in the picture that we had in the slides as well. And now what we're doing is we do Q plots. I divided, as you recall, the entire data to two parts from Jan 2nd, 2014 to May 24, 2016, and then May 25th, 2016 to October 11th. The only reason I did this was because during the first period there wasn't that much changes in the market as far as the rates, and but in the second part we've seen raises in the rates, and I just want to study the relationship between the rates. And as you see here, that's exactly what we had in the slides as well. 1 and 2, you see that they nicely correlated. You see the same relationship between 6, 12. 1 and 12 you don't see as much. They far from each other. 3 and 5 is still you see it, but definitely nothing close to what we're seeing for between 6 and 12. I'm doing the exact same thing for the second half part of it. You have the code, you can play with it yourself. Here is actually much more pronounced. 1 and 2, 6 and 12. 3 and 6 kind of, 1 and 12, between 1 and 12 we don't see that much. You'll see that it's hard to imagine you can pass it through a straight line, but definitely for between 1 and 2 and 3 and 6 you're seeing that, especially between 6 and 12 you're seeing that there is a very nice linear relationship between those two rates. We do now the same thing for the entire data, and still it's very pronounced that you're seeing that between 1 and 2 and 6 and 12 you see this nice linear relationship, and it's almost impossible to see anything between 1 and 12. We do now the same thing for swaps. First we plotting the swap curves on 5 different days. One more time is just we graph just 5 days, but I did it on 5 days that they almost equally distance days, but you can come up with your any day that you want to pick. You have the code, you can play with it yourself, and that's exactly the curve that we had in the slides too. Again, it's important to notice that, for example, the curve in the beginning it was extremely steep, but then it's flattened out. The blue one has to do with is the one corresponds to January 2nd, 2014, and the purple one is actually the one on October 2018, October 11th, 2018. Actually, you see the curve got flattened. Actually, the 30-year rate, you're seeing that actually it's dropped here, but the rest of the curve is actually much higher. Now we look at the time series of it, just seeing that has this been moving together. Let me reduce this to be able to see. You can change it back if you wish. And this is the curve that we already had. Let me make sure that we can, let me see, sorry. That's a curve that we had before as well. One thing to notice that is easy to see, because curve flattened, everything got jammed up, but in the beginning you see they were very scattered, and that's exactly what we see through the curves as well. We're gonna do again the QQ plot to see if we can find any kind of relationship between these rates. As I did it in LIBOR, for LIBOR rates, I would divide the data in 2 parts. I will be focusing on the first part and the second part, and all the entire data all together. Here we see that, for example, for the first half, almost no relationship between any of the rates except for long dated ones. 15 and 30, we see a nice relationship. 2 and 3, even though they both are short dated, short maturity, but still almost no relationship. 2 and 30 completely scattered as if it's completely noise. 5 and 10, you might see that we see some, but there are tons of noise around it. But one more time, 15 and 30, very, very nice relationship between the two. Let's move to the second part of the data. In the second part, the picture changes, especially between 2 and 3. You see 2 and 3 now, we see a very nice relationship between the two. That's something wasn't there in the first half. 15, 30, pretty nice, solid. 5 and 10, something develops, but 2 and 30, again, almost no relationship, none. Now we do this for the entire data on the swap curve. That one, we will see that 2 and 3 on the low rates, almost none, exactly what we had before. But as the rate went up, they get highly correlated. 15, 30, we see that is a nice relationship, linear, but there is a part that depending on the regime, one needs to be careful with this. 510, 230 almost nothing, and 510 it's again it has to do with the time, because we noticed that in the second part it was good, but in the first part of the curve we can't see any relationship between the two. By looking at this, one can come up with a way to relate these two curves, or these two rates, I'm sorry, and maybe infer some information from them. That's something that I will be focusing on the next lecture. Thank you. Welcome to the codes for lecture or module 4. As I said during the lectures, now we explored the linear relationship between some of the rates, and here I'm actually going through it and regressing some of the rates against each other and finding the so-called R-square, seeing how good the fit is by simply trying to use a linear model, linking the two rates together. As usual, we first loading packages, reading data and pre-processing it. The data, as I said before, are swap and LIBOR rates, and for the last 4.5 years. I regress here. I start from 5-year against 2-year. Again, I'm dividing it in two parts. You can do it for whatever interval you wish to. Here I'm doing it regressing 5-year against 2-year from the beginning, which is January 2nd, 2014 to May 24th, 2016. And I just simply do that regression. The regression is pretty straightforward in Python. It's already simply, as you see, we just simply bringing it through setting up X and Y and use the regression to do the fit. And you can easily get the coefficients and R-square as well. Here are the coefficients as I'm having it over here, and this is the R-square, which is exactly what we had in the slides. And you see for the first half of the data, there is almost no relationship. R-square is pretty low, is 4.3%, exactly as I mentioned in the lecture. Now we're doing exact same thing for the second part of the data. For this case, actually, we see a very high, nice linear relationship. These are the coefficients, and this is the R-square, almost 97%. And what I'm doing is I'm using this linear, regression coefficients to build or construct the 5-year from 2-year, because we are having that linear relationship. And I'm plotting it against each other. Then the orange one is the original one. The blue one is a constructed 5-year from 2-year using the regression coefficients. And you see that they nicely follow each other. That's for this part, of course, is been missing a bit, but overall is doing a very, very nice job for the most part of it. We now do this 5-year, 2-year for the entire region. Here we see that R square drops definitely, because you remember the first half we didn't have that much relationship between the two, and you're seeing it exactly here. The second part is much closer, and the R square is just 77%. Now we're doing exact same thing this time, doing a 30 against 15. For the first half, we'll see that R square is 99.5%. Very, very nice relationship between the two, and I plot them against each other. It's nicely done. That's simply showing that they're closely following each other, actually. High correlation between the two. This is for the first half. Let's do this for the second half. The second half, exact same story, 99.5%. And the same as what we've seen before, we construct a series based on 15-year using the regression coefficients against the original, and I'm plotting against each other. The reason I'm doing this is not just for you to see. This is just people using this kind of relationship for coming up with signals, because sometimes that departure could mean something has been overbought or oversold, depending on how you're looking at it, and one can build certain signals. Now that means as soon as you see something happening between the two rates, that could be, that outlier actually is a signal for mispricing. Now I'm doing the whole thing for the entire region now, 30 versus 15, and we'll see the R square goes down slightly from 99.5%, goes down to 95.3%. It's pretty high, but it's not as high as before. And you're seeing that there's certain regions that actually we are under here, we are over here, and that's exactly what's going on. Sometimes we underestimate it, sometimes we are overestimating it. One more time, traders typically, especially technical traders, they use this not in that simplistic way, but this is a good base to see if one can build signals for overpricing or underpricing. What we can do is, as I did it in the slides, as opposed to just regressing one against the other, we can actually regress one against maybe 2 or 3 other rates, or actually even more. Here I'm regressing 30-year versus 2, 5, and 10 for the first part, for the first half, and we'll see that we do a very nice job, 99.4% almost, and they're nicely following each other using 3 rates as opposed to just 1 rate. And you can actually do exact same thing. You can actually add the second part to it. You can have it on the entire region. I leave it to you as a simple assignment. What I'm expecting you to do is that I want you to do exact same thing for LIBOR rates. I just did these things for swap rates, but for LIBOR, you can do it 2 against 1, you can do 12 against 6 for months, or you can do 12 against, say, 6, 3, and 1. I mean, you can exactly mimic what I've done here for LIBOR rates. That's something that I would assign for your assignment. Thank you. 2. By looking at this, one can come up with a way to relate these 2 curves, or these 2 rates, I'm sorry, and maybe infer some information from them. That's something that I will be focusing on the next lecture. Thank you. Welcome to the Python code for Module 5 or Lecture 5. Here, what we are doing is we are as you recall it in lectures, we are now going to go through exact same exercise that we did, but utilizing optimization, both gradient free and gradient base, and then you compare the results with regressions. It's just a simple exercise, seeing that the regression could be also be written as an optimization problem. Here, as usual, we load packages. The data processing is clear, exact same data. I don't even have to go through that. What we are doing is we are using actually First, I go through gradient descent, and for just visualization purposes, as I did in the lecture, I'm looking at the two-dimensional case. First, I build I believe, if I'm not mistaken, I'm doing 5 against 2. Then I'm showing you the surface for the objective function. That's the surface for the objective function. Now I'm looking at the contours for that surface from the top. And when I'm saying the contours, simply means what you're seeing here, they're all at the same level. That means every point on this, they all have the same level. Now, they're all equal. Now, what I'm doing is I'm going to, for the optimization, I'm using gradient descent, as I said, and is a batch gradient descent. That means I'm utilizing the entire data. You can make it mini batch. I mentioned this one earlier. You can do a stochastic gradient descent. I'm just doing here batch. That means I'm utilizing the entire data for it. I'm using for the learning rate, I'm starting from a very small learning rate and assuming max iteration of 300, exactly consistent to what we had in our during our lecture, in our slides. And the starting point is -100 and -100. That's exactly what we had as well. And as I'm running this, that's what you see. The results would be that you're seeing that we start from this point and we're coming in. But as you remember, that would be actually premature stop. That means because the learning rate is too small, it did not converge. And you're seeing that this red line, which is supposed to go through this a bunch of data, didn't actually reach it because, as I said, it was a premature stop. Now we do exact same thing. These are exactly the parameters you remembered in the slides. It stopped, but no way it was optimal. We reached the 300 iterations without reaching the optimal points. Now in this next trial, I'm using actually a learning rate which is a bit higher, exact same starting point. And this time, actually, as you see, we stop at 264. That means we reach even before 300. And you see that this red line is telling us that that's the best possible line that you can pass through the data, 5 versus 2. I repeat this one and these numbers are exactly what you remembered in the slides as well. Now I'm increasing the learning rate, going to now 0.2, just seeing that I can push it to converge sooner. The answer to it is yes. 140, actually, you see that we achieve in just 140. Exact same line, exact same coefficients. You see they're sitting here. I'm pushing it a bit higher now. I'm going to learning rate of 0.3. And you will see that actually the stars, even though it converge in just 95, but you see that it could have actually diverged. Now, and what I'm doing is in the next trial, as you remembered in the slides, I'm pushing it a bit higher, but intentionally in order to visualize it and making sure that it doesn't go too much out of bound, I'm stopping it at after 50 iterations. And when you do this, you'll see that's exactly the case. And as you're seeing that here, we go outside and it start actually completely converging. And no way that this red line is close to the data that we had. Actually, it starts diverging too much that you'll see that it's almost impossible to see the data here. And this learning rate is nowhere actually the rate that we should start. One needs to be very, very careful with what learning rate we work with. Of course, there are optimization toolbox that they come up with adaptive learning rate, like Adam, or there are many of them out there. But it was important for us because I just wanted you to see, even for a very, very simple problem like what we had, which was a linear regression, if you want to use gradient descent, you need to be very, very careful what the learning rate you are using. And also, knowing that if the learning range is not optimal or if it's too small, you may need actually many number of iterations. Otherwise, you would come up with a premature stop, which is no way is optimal. That's exactly consistent to what we had in our slides in the lecture. I mean, you can do exact same thing for 30 versus 15. And then remember, the only reason I used 2 rates was for visualization purposes. You can actually extend this one to 1 rate against maybe 2 or 3 other rates. But if you do it that way, you cannot visualize it anymore. Thank you. Hello, I'm combining the Module 6 and Module 7 Python codes or lectures 6 and 7 because in a way VESECheck and CIR results are pretty similar. It's good to have them just in one, that for you to be able to do the comparison. As you recall, for VESECheck and CIR, we have analytical form for zero coupon bond pricing. And you see in the code, if the model is VESECheck, is much simpler. Here are A and B. You do remember, once you get the A and B, it's very easy to price the zero coupon bond, which simply is what I'm actually substituting over here. In the case of CIR, still the solution is known, the analytical form, but it's a bit more involved. But anyway, you have the code. You can compare it with what I had in the slides. Having said this, then you're getting the, my apologies, then you're getting the model parameters. Whatever model parameter you substitute here, R naught, kappa, theta, and sigma, and then the entire range for tau, you can do simply plug it in, and you get a curve for zero coupon bond for whatever parameter set you're providing. Let's pass this one through. Shift enter here. The same thing over here. And now we come to the data. For the data, I decided, I'm sorry, there were a bit more to discuss here. My apologies, I just jumped a bit. That was for zero coupon bond pricing. Once you have the curve, when you have the zero coupon bond curve, you can use swap rate equation, which are provided in the slides. And then once you have it, you get any swap rate through this equation. And the way I formed it is that you're providing the T range and the P range and the maturities for the swap to say 2, 3, 5, 7, 10, 15, and 30. And then it would give you a range for the swap as well. That means this S is coming is the S that corresponds to 2, 3, 5, 10, 2, 3, 5, 7, 10, 15, and 30. And the same thing for LIBOR rates, exact same thing. I'm exactly implementing what I provided in the slides. The objective function, as you remember, we call objective function to be the the relative error, the score of relative error. On swap, I'm doing it separately. On LIBOR, I'm doing it separately, and I'm adding it up. That's what it is over here. You can play with this one. I mean, for example, instead of having the score, you can do the absolute value. This is absolutely up to you. You can play with this yourself. My apologies. And as you see, once I'm coming inside the objective function, then I'm already, because I passed already the, I already know the zero coupon curve, I'm simply passing it to get the market ones. These are, let me make sure that I'm correct here. Yes, these are becomes the model, my apologies, SNL. Then the other ones are the market. And as I said, I'm looking at the relative error, which the goal is to minimize the distance between the model and the market. That's fine. And for calibration, what I'm doing is I'm actually passing here Nelder-Mead as opposed to any gradient descent. I'm using Nelder-Mead here. You can change it to some other optimization routine. That should be absolutely fine. Now the market rates, I'm picking 2 different dates. You remember in the slides I have this. For the 1, 2, 3, 6, and 12 months, I'm having 2 snapshots. I actually could have put this one down here to be able to do it, to visualize it nicer. Let's see. could have done it like this. Sorry about this. Good. Then as you're seeing, the first column here is the maturity. This is for one of the days. This is for the second day. The same thing here. The maturity for swaps, the swap term, the first day and the second day. These are the snapshots I'm having. The second column corresponds to one of the days, and the third column corresponds to the other day we have in mind. You can go through the data yourself and just pick any days that you wish. Let's pass this through as well. Now for the parameters, a starting point is important. I'm assuming the following starting point, I'm using the same starting point for both of them. This is for V naught, this is for kappa, theta, and this is for sigma or lambda. Depends on exactly, I'm putting it actually up here what they are. Let's pass this one through too. Now then for vessel check, as I said, I'm assuming 2 different days. For vessel check model, for the first day, I'm passing the objective and I do my optimization. It was done very quickly, and this is the parameters I'm getting out. For the second date, exact same thing. I'm doing that one, run the optimization, and this is the parameters I'm getting. I'm doing exact same thing for CIR as well. For the first date, for the second date, you have the code, you can play the code, that should be easy. As you're noticing here, when I'm saying which day, then I'm going and picking the corresponding column, because I know the third column corresponds to one of the days, second column corresponds to the first day that I'm picking. And what I'm doing is now, the one that I did for the first day, which is December 14, 2017, I simply do plots, and the plots are, the first plot is what's coming out of the calibration, the curve for zero coupon bond. The second and the third are LIBOR and swap rates respectively, and let me make sure that that's the case. Let me go through it before I, the first one are the curve, the blue curve are the market, and the orange ones are the model. And as you see, one would expect the same thing. It doesn't mean you would perfectly match it, because that's calibration. You've seen that we're doing a relatively good job on the short term. Here we missed. Then on the other hand, over here, we did a very nice job on the 10, but we kind of, overestimated here and underestimated there. There's always a trade-off when you do the fit. This is the one that we do for October 11, 2018. Let's see how well we did here. We did actually slightly better here. For the LIBOR, we did a good job. For the swap, kind of, again, we did a nice job on the 10 and the 30, but we underpriced the 15 and overpriced actually 5 and 7, and that's the corresponding curve. Let's do the same thing for, and then I'm plotting actually the curves for 2 days. The one, let me plot this one. This is for vessel check. The orange one corresponds to October 11, 2018, and the blue one, December 14, 2017. As you see, because the rate been going up, October 11, 2018, actually the curve is lower. That's exactly what we had in the module first. The first module, if you remember, as the rate goes higher, the curve starts going down faster. That's trivial. We do exact same thing for CIR. For the CIR, the fit is relatively close to what we've seen for vessel check. Some underpricing, some overpricing. This is for LIBOR, the fit for LIBOR and swap. That's its corresponding curve. On October 2018, do that calibration. It does slightly better now. LIBOR, relatively a good job. On the swap, does a very nice job on 2 and 3, 10 and 30, but we underprice 15 and overpriced 5 and 7. One more time, of course, this is a very, very simplistic model, but this missing sometimes is a sign from perspective of signal traders that but of course you need just one snapshot is not enough. You need a time series of it. You need the cross-section, and cross-sectional analysis is a sign for good mispricing, or maybe market being overbought or oversold, or something is cheap or something is rich. Now let's do the comparison between the two. Again, between these 2 days, that's CIR consistent to what we had from Vasicek as well. You can also compare the two models against each other, both Vasicek and CIR. I leave it to you. That should be pretty easy to do. But as you remembered in the slides, they do, for these 2 days, actually they're pretty consistent. That means no matter you would have used Vasicek or CIR, you would have gotten the same results. This is not always the case. This is not always the case. It turned out to be that case. But then definitely you can try it. And I'm going to actually assign something for your assignment or homework that we pick other days because you have 4.5 years of data. We can go maybe to January 2nd, 2014, and you'll see if you do it yourself. And it's very, very easy to do. It's a matter of just simply going up here and replacing. Is as simple as that. Simply replacing this column with January, this one, and that one with the one on January 2nd, 2014. I could have done it, but I want to leave it for you because I want you to do a comparison between Vasicek and CIR. Now you have the tool, you have all these tools that you can simply setting it up, playing with the objective function, playing with various different days, and do the fit and see, even with one factor, with some very, very simplistic model, we can still do a relatively good job fitting the curve. That was my goal, at least for this lecture. Thank you so much.